Hello, friends. IBM is here with another episode of Solved Past Paper Questions. This is part 3 of electromagnetic fields and electromagnetic induction. And I hope this will be the last part, although it might be longer, but I pray that it will be the last part of these solved past paper questions so that we now move to alternating current. Alternating current will be cheaper and shorter, so that won't take much time. It could be like 1 or 2 episodes. So let's actually move to our document. I think in part 2, we must have stopped on page around 216. So let's move to back to our document. Let's move back to our document of solved past paper questions. Yes, we are here. In part 2, I think we stopped on this graph, which we actually sketched. And I want us to start straight away from the next question. The question is explain, let me get a pen which is thinner. Explain the use of uniform electric field and the uniform magnetic field for the selection of the velocity of a charged particle. You may draw a diagram if you wish. Normally drawing a diagram makes life very easy. So let me show you how to draw a diagram which makes life easy. You need a uniform electric field, therefore you will draw parallel plates. Parallel plates, that is a uniform electric field. I can say the upper plate is positive, and I will say the bottom plate is negative. That means the field is downwards. So I'm going to choose the sign of a charge for easy understanding and let the charge be positive, entering the uniform electric field with speed v. When the charge enters the field, of course, it is going to experience a force due to the electric field that is downwards. So the force due to the electric field on the charge is going to be downwards. I must find a force due to the magnetic field that should be upwards. So I must find a force due to the magnetic field that is upwards. So I am going to introduce a magnetic field into this same region so that the force due to the magnetic field is in the opposite direction to the force due to the electric field. And by Fleming's left-hand rule, this is going to be actually into the page. So I'm going to draw a magnetic field into the page is represented by a circle with a cross. So this is the B field which is into the plane of the page. So if these two forces, if the fields are adjusted so that the force due to the electric field is balanced with the force due to the magnetic field, then a particle whose velocity v is equal to E over B is going to be selected. So I will simply write a few statements here, or even 2 statements, and I say the fields are adjusted. Fields are adjusted. The fields are adjusted so that Fe, that is the force due to the magnetic field, is balanced with the force due to the electric field, which therefore implies that BQV will be equal to Q times E, that is the force due to the magnetic field is equal to the force due to the electric field. And for no deflection, then it means V is going to be equal to E over B. That will be the particle. Those are the particles that will be selected. So this simplifies everything. Of course, you have to use a ruler and draw a very neat diagram. Okay. Ions are all of the same isotope. Ions, all of the same isotope, are traveling in a vacuum with a speed. The speed is 9.6 times 10 power 4. The ions are incident normally on a uniform magnetic field. Flux density is 640 milliteslas. The ions follow a semicircular path as shown here. Reaching the detector, data for the diameters, they have given us data for the diameters. and we see that the diameter of B is twice the diameter of A. The ions in the path B each have a charge of positive 1.6 times 10 power negative 19 coulombs. Determine the mass in U of the ions in path B. So we know that the magnetic force FB provides the centripetal force, FC. So I'll just say BQV is equal to mv squared over r. We want to find the mass. So I'm just going to make the mass the subject. So the mass is going to be equal to B QR divided by V, because one V cancels out. Then when I substitute, I'll substitute straight away. Remember, we had the magnetic field above, the magnetic flux density was 640 millitesla, so it will be times 10 power negative 3. The charge is 1.6 times 10 power negative 19. The radius is, because for B they have given us the diameter as 12, so the radius is 6.2 centimeters. So that will be times 10 power negative 2 to change it to meters. Divide by the speed. They gave us the speed above as 9.6 times 10 power 4. So I press my calculator. So from my calculator, I'm getting the mass in kilograms as 6.61 times 10 power negative 26. Of course, this is in kilograms. I'm going to divide this by 1.66 times 10 power negative 27 to change it in the unified atomic mass units. Remember, 1U is 1.66 times 10 power negative 27 in kilograms. So you have to change in unified atomic mass units. 6.61 divided by 1.66. So this is giving me an answer which is approximately 39. This is 39.8. Of course, the mass in U can always be written to one significant figure. It's only the mass in unified atomic mass units and the absolute uncertainties that are normally quoted to one significant figure. So this is approximately 40. Suggest and explain quantitatively a reason for the difference in the radii of the paths A and B of the ions. We see that the path B is twice in diameter, or the radius of B is twice the radius of A. And we notice that actually charge, if we look at the charge to mass, we look at the charge to mass ratio. Charge to mass, if I make Q over M the subject, Q over M is going to be equal to V over R times B. So we notice that the charge to mass ratio is directly proportional to 1 over R, or it is inversely proportional to the radius. And so we can say that if the mass is constant, if the mass is the same, then and yet we are seeing that Q over M is directly proportional to 1 over R, or Q is inversely proportional to R. So we notice that Q over M for A is going to be twice. If the mass is the same, if the mass is constant, so if M is constant, and we are seeing that it means that still Q is inversely proportional to R. So it implies that Q over M for A is going to be equal to twice, is going to be actually twice, that of B, that for B. Because the radius of B is twice that of A, so it means the charge to mass ratio of A is going to be twice that of B. After all, charge is inversely proportional to radius. So the charge over mass for A is twice that for B. And note that if the ions have the same mass, but if ions in A have the same mass as that in B, but twice the charge of the ions in path B, then there should be a difference in the radii. So we are saying the ions in path A have the same mass, but twice the charge. The ions in path A may have the same mass as those in the same mass as those in path B, have the same mass, but twice the charge of ions in path B. So we can think about that in that way, because if the paths are showing that the charge to mass ratio of A is twice that of B, it is only because if the mass is the same, then the charge of A should be twice the charge of ions in path B. That's what the radii are actually dictating. Okay, suggest two wires are laid side by side and carry equal currents I in opposite directions as shown in the figure. The total magnetic flux density due to the current in the wire is negligible. Suggest an explanation for each of the following observations. The two wires are laid side by side, but they are saying the total magnetic flux density B in the wires due to the current in the wires is negligible. I think this is obvious. If it is negligible, you just use the right hand grip rule. Use the right hand to grip a pen in your hand and the thumb points in the direction of the currents. You notice that the current due to this one is causing a field in one direction. It could be making the fingers fold upwards. And the current in this one, when you grip your pen, you reverse the direction of the thumb. The fingers are folded downwards. It means the fields are in opposite directions. And if the currents are the same in magnitude, then the fields are equal in strength. Therefore, if they're in opposite directions and they're equal in strength and they're in the same area, then they are cancelling out each other. So we simply say that the magnetic fields are equal. The magnetic fields are equal in strength. The magnetic fields are equal in strength. Therefore, we have the same flux density. They have the same flux density, but they are in opposite directions. But are in opposite directions. But they're in opposite directions. So the fields cancel to give us zero or negligible. They cancel out to give a zero or negligible resultant field. So that is it. Magnetic fields are equal in strength, same flux density, but they're in opposite directions. So the fields cancel. Oh, the spelling of cancel, there is an L, I think. The fields cancel to give a negligible resultant field. An air-cooled solenoid is connected in series with a battery as shown. As an ion core is inserted into the field, an EMF that opposes, that is Lenz's law. An EMF that opposes the EMF of the battery is induced in the solenoid. So we have to explain this observation. Why is there an EMF that opposes the EMF of the battery induced in the solenoid? So when we insert the core, what happens? The purpose of the core is to increase the magnetic flux. So we are saying the core increases. The core causes increase. The core causes increase in the magnetic flux. The core causes increase in magnetic flux. The core causes increase in magnetic flux in the solenoid. And remember, a changing magnetic field, because it is increasing, it is actually changing. And remember, a changing magnetic field, a changing field is going to induce, or a changing field is going to be induced in the core. So the core causes increase in magnetic flux in the solenoid. So therefore, there will be a changing field induced in the core. So, and a changing field. A changing field is induced in the core. A changing field is induced in the core. Of course, when there is a changing field in the core, or there is a changing flux in the core, this also cuts again the turns of the solenoid. So we are saying again that the changing flux in the core cuts or threads the changing flux in the core. Changing flux in the core cuts the turns of the solenoid. The changing flux in the core cuts the turns on the solenoid. Cuts the turns on the solenoid. The changing flux in the core cuts the turns on the solenoid, and by Faraday's law, an EMF is induced. An EMF is induced in the solenoid. EMF is induced in the solenoid. Then you think about Lenz's law. Now, an EMF has been induced in the solenoid due to the changing magnetic flux in the core. By Lenz's law, this EMF acts to oppose. This EMF opposes or acts to oppose the battery EMF. That EMF acts to oppose the battery EMF. Think about it. So note the process. The core causes an increase in magnetic flux in the solenoid when it is inserted there. Therefore, there is a changing field induced in the core because of the changing flux in the solenoid. A changing flux in the core also cuts the turns of the solenoid, and by Faraday's law, an EMF is going to be induced in the solenoid due to the changing flux in the core again. By Lenz's law, this EMF tends to oppose or creates an effect that tends to oppose the change producing it. In other words, this EMF opposes the battery EMF, and this is making the current in the flowing to be smaller or to reduce. It is causing the EMF of the battery to be actually affected. Okay. A particle has mass m and charge q and speed v. State the magnitude and direction of force, if any, on the particle when the particle is traveling along the direction of a uniform gravitational field. Of course, when the particle is traveling along the direction of a uniform gravitational field, the force is just m times g, where g is the acceleration due to gravity. Therefore, the direction is along the field. It moves along, the force is along the direction. The force is along the direction of the field. Remember, the force due to masses is attractive. So the force is going to be just along the direction of the field. Then the particle is entering a uniform magnetic field of flux density B. So a particle has a mass m, charge q, speed v. If state and the magnitude and direction of the force, if any, on the particle when the particle is traveling along the direction of a uniform magnetic flux density B. So here there will be no force, because for the particle to have a force, its speed should have a component normal to the magnetic field. Now here, if its speed is just along the field, the direction of the field, then there is no force. So the force there is zero. So since there is no force, we can't talk about direction. Okay. Two charging horizontal metal plates situated in a vacuum produce a uniform electric field of field strength E between the plates. The field strength outside the region between the plates is zero. Outside is zero. The particle in A enters the region of the electric field at right angles to the direction of the field as shown here. So it is a positively charged particle. So it is experiencing a force due to the electric field downwards because the particle is positively charged. A uniform magnetic field is to be applied in the same region as the electric field so that the particle passes undeviated. So there should be a force on the particle when it enters the field to oppose or to balance with the force due to the electric field that should be acting upwards. The force due to the magnetic field should be acting upwards. State and explain the direction of the magnetic field. Of course, using Fleming's left-hand rule, we now know that the particle is moving to the right, so the second finger points to the right, and the thumb should be pointing upwards. If the second finger is pointing to the right with your hand resting on the table with the three fingers at 90 degrees, the second finger is pointing to the right. When you are facing your paper, the thumb is pointing upwards. You just want to rotate the hand so that the thumb points to the paper. I mean, the thumb points up of the page or away from you. So when you rotate your hand through 90 degrees, you notice that the thumb points upwards, the first finger points to the page or onto the paper. So that means by Fleming's left-hand rule, the magnetic field is going to be into the plane of the paper. So one, we know that the force due to the electric field, I'll just use Fe, is downwards. Two, we know that the force due to the magnetic field should therefore be upwards. Fb must be upwards. Fb must be upwards, and by Fleming's left-hand rule. By Fleming's left-hand rule, if Fb is upwards, the thumb points up the page. That is away from you. If you are facing your page on table, away from you, that's where the thumb points. The second finger must point to the right. If the thumb points upwards with the second finger pointing to the right, my first finger is pointing onto the table, onto the question paper, onto my computer on the table. So that means the field is into the plane of the paper. So field is into the plane of the paper. The field is into the plane of the paper. Okay, number next, derive an expression. Derive with explanation. Derive with explanation the relation between speed and the magnitudes of the electric field strength, E, and the magnetic flux density, B. So if the particle passes through undeviated, it means the force due to the magnetic field, the force due to the magnetic field is equal to the force due to the electric field. The force due to the magnetic field is equal to the force due to the electric field. So this is going to be B QV is equal to Q times E, which therefore gives us V as E over B as required. A second particle has the same mass. Second particle has the same mass as the first particle. Same mass and charge Q as that in B, but it has speed twice. So if the speed is greater, the second value of speed twice V is greater than the first value of speed. This is because the force due to the magnetic field is greater than the force due to the electric field. That's what it means. And therefore, the particle is experiencing a resultant force in the direction of the force due to the magnetic field. Sketch the path of this particle in the region between the plates. So we come here. Because the resultant force is upwards, so we shall draw a parabolic path. We shall draw a parabolic path. It should be a very neat parabolic path. And of course, after, because there is no field outside, outside should be a straight line. Outside here, it should be straight. So use a ruler and draw a very nice thin tangent, a very nice tangent to this curve. A very nice tangent. After the field, you put a line, a straight ruler, and draw a very thin, nice tangent. Your graph should not be crooked, should not be kinked. It should be just a smooth curve, where the curve is a tangent to this part here, and it is also tangent. There's a tangent, a straight line which is a tangent to the curve when it is emerging. Okay. Next, state the type of field or fields. State the type of field or fields that may cause a force to be exerted on a particle that is uncharged. If the particle is uncharged, the only field which is acting must be gravitational. Because as long as it has mass, gravitational force is there. So it means even though the particle is charged, the gravitational force is always there, as long as it has mass. So there is gravitational, whether it is moving or not, there is gravitation. Okay, but now this one is charged and stationary. So on addition to gravitation, there is also electric because it is charged. There is electric fields. Because it is stationary, it only has gravitational and electric fields. Those are the ones which are acting or which will cause a force. Now here it is charged, so it means there is also electric field. But now it is moving at right angles, so the force due to the magnetic field is maximum. So here there is also magnetic. So if the particle was moving again parallel to the magnetic field still, the magnetic field will not exert any force even though the particle will be moving. Okay. A particle X has mass. The mass is 3.32 exponent negative 26 and the charge is positive 1.6 exponent negative 19. The particle is traveling in a vacuum. Speed is 7.6 times 10 power 4. It enters a region of uniform magnetic field that is normal to the direction of travel. The particle travels in a semicircle of diameter 12.2 centimeters as shown here. So we see the particle is traveling that semicircle. State the direction, state its direction, state its direction. So for a uniform magnetic field in which the particle is entering, state the direction. First of all, you see that the same circular path is showing that the force is always acting towards the center because it is causing centripetal force. So at the point of entry here, the force due to the magnetic field is in that direction and the particle is moving in that direction. So the first finger is what we are looking for, the direction of the field. This direction here of FB is where we point our thumb. Your thumb should point to the right. Then the second finger, which shows the direction of motion of the particle, because it is positive, the second finger points in that direction upwards. So make the second finger point upwards with the thumb pointing to the right. You notice that the first finger is pointing to the roof. Make the first finger pointing away from you, that is up of the page. With the thumb pointing to the right, you notice that the first finger is to the roof. If the second finger is pointing away from you, with the thumb pointing towards the right, the first finger is pointing to the roof. If you're holding your hand with the elbow resting on the table, that is what you're getting. So it means the field is out of the plane of the page. That is by Fleming's left-hand rule. So by Fleming's left-hand rule, the field is out of the page. It's out of the plane of the page. It is out of the plane of the page. It is not upwards. It is out of the plane of the page. If your page is resting on the table, you must have seen that. Calculate the magnetic flux density. Calculate the magnetic flux density. So we know that the magnetic force Fb provides the centripetal force Fc. So we just equate BQV to mv squared over r. And we want B. We want B, so B is going to be equal to mv divided by r times q, or qr. We now substitute. Magnetic flux density is going to be equal to m was given as 3.32 times 10 power negative 26. We saw the speed of the particle was 7.6 times 10 power 4, and we have seen the charge was positive 1.6 times 10 power negative 19, and we have seen the radius is, the diameter is 12.2, so the radius is 6.1 times 10 power negative 2. So I press my calculator. So from my calculator, the magnetic flux density is 0.26 teslas. The second particle Y has mass less. The mass is less than that of X and has the same charge. The charge is the same. It enters the region of uniform magnetic field with the same speed, so V is the same, along the same initial path. Draw the path of the particle y in the region. So from this expression here, we notice that B is equal to mv over q times r, or B qr is equal to m times v. If B, Q are the same and V is the same, it means it is only R being affected with M. So it means R is directly proportional to M. Since it has a less mass, so the radius of the path should be smaller. Therefore, we come back here and sketch a path which has a smaller radius. So it enters the same initial point, so the path should have a smaller radius. Draw a path which has a smaller radius. Let me draw a better one. So that is the new path, because the radius is directly proportional to the mass. So because the mass has becomes smaller, then the radius should also be smaller than the one which is already there. Okay. A solenoid is connected in series with a resistor as shown here. As the magnet is being moved into the solenoid, thermal energy is dissipated in the resistor. Thermal energy is dissipated. Use laws of electromagnetic induction to explain the origin of thermal energy. Where is the thermal energy being got in this case? So the magnet is moving. It is being moved towards the solenoid. So the moving magnet gives rise to an EMF or a current in the solenoid because it changes the magnetic flux. So the moving magnet gives rise to an EMF. An EMF, thus a current in the solenoid. It gives rise to an EMF, thus a current in the solenoid. The induced current now is going to create a field in the solenoid. The induced current is going to create a field in the solenoid. The induced current creates a field in the solenoid, and this field opposes the motion of the magnet. That opposes the motion of the magnet. So the magnetic field which is created in the solenoid tends to oppose the motion of the magnet. So it means work is going to be done. Work is done to move the magnet into the solenoid. Work is done to move the magnet into the solenoid. This is now against the repulsion. Work is done to move the magnet into the solenoid against the repulsion. And the induced current is the one which is going to give the heating effect in the resistor, which is going to be coming from the work done. So the induced current or an induced current, work is done to move the magnet into the solenoid against the repulsion. and an induced current. Induced current gives a heating effect. The induced current gives a heating effect in the resistor, which comes from, or which is derived from the work done, which comes from the work done. Okay, so that's why there is thermal energy in the resistor. Initially, the magnet is moving, which is giving rise to an EMF in the solenoid. And then again, when there is an EMF in the solenoid, the induced current in the solenoid creates a field around the solenoid, and this field tends to oppose the motion of the magnet. So work is going to be done to overcome that opposition. And of course, when work is done, it means there is an induced current which gives a heating effect in the resistor. Which induced current is coming from the work done in overcoming or in opposing the motion of the magnet. That is conservation of energy as Lenz's law. Okay, next, explain why alternating current in the primary coil of a transformer is not in phase. That is a very simple question, but quite technical. The alternating current is not in phase. Of course, we know the primary coil produces a magnetic field around it, which is exactly in phase with the primary current. But then remember, by Faraday's law, an EMF is induced when there is a change in magnetic flux. The change in magnetic flux linkage cannot be the same as, cannot be in phase with the magnetic flux. Because when the magnetic flux is maximum, the change is zero. And when the magnetic flux is zero, the change is maximum. So they are always out of phase. Therefore, we can say the current in the primary coil, current in the primary coil the current in the primary coil gives rise to a magnetic field in the core. Gives rise to magnetic field in the core, which is in phase. Which is in phase with the current in the primary coil. So the current in the primary coil is giving rise to a magnetic field, or a magnetic flux, which is in phase with the current in the primary coil. But the magnetic field or the magnetic flux links with the secondary coil or cuts the secondary coil. The magnetic field, or the magnetic flux links or cuts the secondary coil. Links or cuts the secondary coil, inducing an EMF. Inducing an EMF in the secondary. By Faraday's law, the EMF induced by Faraday's law, the EMF induced is directly proportional to the rate of change. The rate of change or the rate of cutting, the rate of change of flux. So it can't be in phase. So not in what? Not in phase. So you just need to know the logic here. Current in the primary produces a magnetic flux in the primary, which is just in phase with the current in the primary coil. The magnetic flux spreads to the secondary coil, which is inducing an EMF in the secondary coil. But remember, by Faraday's law, an EMF is induced when the rate of change, when there is a change in flux linkage with time. And the induced EMF is depending on this rate. When the flux linkage is maximum, the rate of change is zero. And when the flux linkage is zero, the rate of change is maximum. So they cannot be in phase. Therefore, we are saying the induced EMF is not in phase with the primary EMF. Two long straight wires, P and Q, are parallel to each other as shown in the figure. There is a current in each wire in the direction shown here. The pattern of the magnetic field lines in a plane normal to the wire P due to the current in the wire is also shown here. Draw arrows on the magnetic field lines in the figure around wire P to show the direction of the field. So you just grip your pen with the thumb pointing in the direction of the current. You notice that the fingers are folding anti-clockwise. So it means the field is anti-clockwise. That is the right-hand grip rule. Then determine the direction of the force on the wire Q due to the magnetic field from wire P. Since the two wires are carrying current in the same direction, then you remember the pinching effect. So wire Q is experiencing a force towards wire P. So this is the pinching effect. So we can say they say the direction of the force on wire Q due to the magnetic field from wire P. So this is to the left. It is attracted towards wire P, so it is to the left. Then the current in wire Q is less than the current in wire P. State and explain whether the magnitude of the force on wire P is less than, equal to, or greater than. So remember, by Newton's third law, by Newton's third law of motion, the force is the same, they are equal but opposite. By Newton's third law, the forces are equal but opposite, because each force is due to the magnetic field of another wire. However, we can also explain this by thinking of the fact that the force between the two wires depends on the product of the currents. So the force is the same. The force depends on the product, or is the force is directly proportional to the product of the two currents. And the product is always the same, so the force is the same. Or the force is equal. So the force is the same or equal. Okay. Next, define magnetic flux linkage. Define magnetic flux linkage. Define magnetic flux linkage. Of course, from calculation, you now know that flux linkage is NBA. So we can simply define magnetic flux linkage as the product of the number of turns flux density, flux density or magnetic flux density, and let me make this one very complete. Magnetic flux density and the area normal and the area normal to the magnetic field. So that is the magnetic flux linkage, that is NBA. The product of the number of turns, the magnetic flux density, and the area normal to the magnetic field. A solenoid of diameter 6 centimeters, 5540 turns, is placed in a uniform magnetic field, as shown here. The variation with the time t of the magnetic flux density, as is also shown in on the graph here. Calculate the magnitude of the induced EMF in the solenoid. The variation with the time t of the magnetic flux density is shown here. Calculate the magnitude of the induced EMF in the solenoid. So the magnetic flux density increases from 0 to 250 at a time of this is actually 2.4. That is 2.4. It remains constant, and then it decreases from 250 up to 0, back to 0 in a time of, this is from 6 to that point, that is 1.2. So notice that this time is smaller than this one, so this one is giving us the maximum magnitude of the induced EMF. So we know that induced EMF is equal to NBA over time, or is the rate of change in magnetic flux linkage with time, delta t. So this is going to be the number of turns is given as what is the number of turns? 550. So we have 550. The magnetic flux density is 250 millitesla, so that is 250 times 10 power negative 3 minus, of course, from that to 0. Then the area they gave us, I think they gave us the radius. The diameter is this, so the radius is 3. The area is going to be pi r squared. So this is going to be times pi times the radius, which is 3 times 10 power negative 2, and this is squared, divided by the time. Because I'm looking for maximum, the time should be smallest. So this is going to be 1.2 seconds, not 2.4. Because I'm looking for the maximum magnitude, then the time should be smallest. I'm pressing my calculator. So from my calculator, I have the EMF as 0.32. A thin copper sheet X is supported on a rigid rod so that it hangs between the poles of the magnet as shown in the figure. Okay, so we have this, we have a rigid support. A rigid rod is supported by a copper sheet, as we can see. Sheet X is displaced. Sheet X is displaced to one side and then released. X is displaced to one side and released so that it oscillates. Note that it will be oscillating between two poles of a magnet. A motion sensor is used to record the displacement of X. A second thin copper sheet Y replaces sheet X. You notice the difference between this sheet Y and sheet X. In sheet Y, they have the same overall dimensions, but sheet X was solid. This one has some parts which have been cut out. You see, there are these parts which have been cut out. That means there is actually going to be a decrease in flux linkage. The motion sensor is again used to record the displacement. The graph in the figure shows the variation with the time t of the displacement s of each copper sheet. State the name of the phenomenon illustrated by the gradual reduction in amplitude of the dashed line. So gradual reduction in amplitude, that is light damping. Gradual reduction in amplitude, that is called light damping. We saw that in simple harmonic motion. Light damping. Damping is the reduction in the amplitude due to dissipation of energy. Deduce which copper sheet is represented by the dashed line. Explain your answer. When we look at the nature of these, when we look at the nature of these, we notice that actually this one here, which is copper, the induced EMF in Y is going to be smaller. Therefore, because it has been some parts have been cut out, even though the overall dimensions are the same, it has been cut out into this shape, so it is reducing the magnetic flux linkage. Therefore, the induced EMF in it is going to be smaller, so the force opposing its motion is going to be less than it would be for copper, where it is solid. It is fully, for X, where it is completely solid, the induced EMF in this one is larger because there are no missing pieces, so it experiences a larger force that slows it down. Therefore, I think the solid line is most likely going to be X, and the dotted line, the dashed line, is most likely going to be, the dashed line is most likely going to be X because the induced EMF is larger, and the solid line is most likely going to be Y because the induced EMF is smaller. So there's more damping for a solid line. For X, there's less damping for Y. That's what this is going to mean. Therefore, we are saying the copper sheet cuts the magnetic flux. Because it's 4 marks, we have first of all to explain using the principles of electromagnetic induction. So we are saying the copper sheet cuts the magnetic flux and causes an induced EMF. So there is an induced EMF in both. But the induced EMF is going to cause, of course, eddy currents. The induced EMF causes eddy currents. The induced EMF causes eddy currents in the sheets, in both sheets, of course. What does the current do? The current in either sheets dissipate energy. The currents in the sheets they can also cause resistive force according to Lenz's law. Or maybe let me use the first part. So the eddy currents in each sheet, the eddy currents dissipate energy. The eddy currents in the sheets dissipate energy. If the eddy currents dissipate energy, it would mean more energy is dissipated in X than it is in Y. More energy is dissipated in X than it is in Y. So it means for these graphs here, X must be the dotted line because of more damping than in Y. So we are saying the eddy currents in the sheet dissipate energy. The eddy currents in the sheet dissipate energy. but there is small current in Y and a large current in X. There is a smaller current in Y. So the solid line, so the dashed line is X. Okay, so we can talk about that, or we can still say the currents in the sheet cause resistive force. The current or the currents in the sheet causes or cause resistive force. That is in accordance with Lenz's law. And since there is a smaller current in Y, then there is a smaller resistive force. Therefore, the dashed line is still X. So I can still say the currents in sheet cause resistive force, but there is smaller current in Y. So the dashed line is still X. So you can explain in terms of resistive forces caused by the resistive forces caused by the currents, that is in accordance with Lenz's law. Or you can think about the currents dissipating energy. More energy is dissipated in X than it is in Y because of the shapes of these conductors. Okay. State what is meant by a magnetic field. So by the way, for X, because there is a large current, there is more energy being dissipated. The damping is high, there is much damping. For Y, because there is a small current, there is less energy dissipated. So there could be almost no damping. Therefore, the dashed line was still for X. Okay, state what is meant by a magnetic field. I'll just consider a magnetic pole. And we say this is a region of space. This is a region of space where there is a force due to there's a force due to or exerted on a magnetic, I'll just say magnetic pole. It can be due to a current carrying conductor. It can be due to a moving charge. So that is a magnetic field, a region of space where there is a force, where a force is experienced by or due to, where a force is created by or due to a moving charge, a current carrying conductor, a magnetic material, a magnetic pole. That is a magnetic field. A rectangular piece of aluminium foil is situated in a uniform magnetic field of flux density B, as shown here. So you can see the flame. The magnetic field is normal to the face PQRS of the foil. The electrons, each of charge negative Q, enter the foil at right angles to the face PQTV. On the figure showed is the face of the foil on which the electrons initially accumulate. Explain why the electrons do not continuously accumulate on the face you have shaded. Of course, if you are now familiar with this, you notice that the electrons are going to accumulate on this side here, PQRS. Why? Using Fleming's left hand rule, hold your paper vertical, standing on your table. Let the paper be vertical. Let it be facing you. Just when you are sitting upright, the paper is vertical. With the first finger pointing downwards in the direction of the field of the left hand. And the second finger is supposed to point in that direction, but this, since they are electrons, you rotate your hand so that the second finger now points in the direction, on the opposite direction to that of the electrons. That is, it should be pointing to the left. You are going to notice that the thumb is pointing downward. The thumb is pointing towards you. If your paper is vertical, with the first finger pointing downwards, because the field is downwards, and instead of the second finger pointing to the right, you rotate your hand so that it points to the left through 180 degrees. When you do that, with the first finger still downwards facing towards the table, rotating your hand so that the second finger points in the opposite direction to that of the electrons, the thumb is pointing towards PSWV. Therefore, that's why we are shading this part here. That is by Fleming's left-hand rule. By Fleming's left-hand rule. By Fleming's left-hand rule. Explain why the electrons do not continuously accumulate on the face you have shaded. Of course, as electrons accumulate here, the positive ions will be on the other end. Therefore, there will be a potential difference created between the other end and this other end we have shaded. This therefore implies that an electric field is created between the two opposite faces. An electric field would mean that an electron X, which is at some point between here, is experiencing two forces. There's a force pushing it towards that end due to the magnetic field, and there will be a force pushing it towards high potential due to the electric field. When those forces balance, then the electron cannot move to any of the two sides. Therefore, the accumulation of electrons stops instantly. Therefore, we are saying that the accumulation of electrons the accumulation of electrons or let me say the accumulating electrons, cause an electric field. The accumulating electrons cause an electric field between the faces. The force due to the electric field is going to be opposing the force due to the magnetic field. So the force due to this electric field opposes the force due to the magnetic field. The force due to the electric field opposes the force due to the magnetic field, and the accumulation of electrons stops when the magnetic force equals the electric field. And accumulation of electrons stops when the force due to magnetic field equals the force due to electric field. So the accumulation will stop when FB is equal to, that is when FB is equal to FE. The electric force is equal to the magnetic force. Accumulation of electrons will stop. But before that happens, more electrons will move towards PSWV, and more positively charged ions will move towards the other end of QR, and the PD is continuing to develop, which is going to be called the Hall voltage. Okay, the whole voltage VH developed across the foil in B is given by this expression here. You should now be familiar with it. State the meaning of the quantity n. We know that n is the number density of charge carriers. Number density of charge carriers. Number density of charge carriers, or the number of free electrons per unit volume, or the number of free electrons the number of free electrons per unit volume. Using the letters on the figure, identify the distance t. So t is supposed to be thickness. And from the figure, t can be PV, it can be SW, it can be QT. That is P, that is T, which is the thickness. So we are going to say it is either PV, or it can be QT, or it can be SW. Of course, you can't state all of them, just state one. Suggest why in practice the hole props are usually made using a semiconductor. Why a semiconductor material rather than a metal? We have already seen that for a semiconductor, N is much smaller, so VH is much larger. So for a semiconductor, N is much smaller. N is much smaller, so VH is much larger and measurable. So it is easier to measure. If for a semiconductor, N is much smaller, so VH is much larger and measurable. Okay, state Lenz's law. Remember, Lenz's law deals with direction. So the direction of the induced EMF is always such as to cause effects that oppose the change producing it or causing it. So Lenz's law, the direction of the induced EMF. Direction of the induced EMF is such as to cause effects that oppose the change causing it, or to oppose the change producing it. That is Lenz's law. A metal ring is suspended from a fixed point P by means of a thread, as shown here. Okay, the ring is displaced a distance d and then released. The ring completes many oscillations before coming to rest. The poles of a magnet are now placed near the ring so that the ring hangs midway between the poles of the magnet, as shown in the figure, as shown here in this figure here. The ring is now in between the poles of the magnet. The ring is again displaced a distance d and then released. Explain why the ring completes fewer oscillations before coming to rest. So now here the ring is supposed to be oscillating the magnet. In the first case, when there was no magnetic field, it was making many oscillations. So explain why the ring completes fewer oscillations before coming to rest. Of course, that is the principle that we're now applying either Faraday's law and Lenz's law to explain that. Okay, so number one, let me see, 1, 2, 3, 4, 5, 6 lines. I think they are enough. So we are going to say because the ring is moving, the ring cuts the magnetic flux. So the moving ring cuts the magnetic flux. It cuts the magnetic flux of the magnet, which causes induced EMF in the ring. Which causes induced EMF in the ring. What does the induced EMF do? The induced EMF is going to cause eddy currents. So the induced EMF causes eddy currents. In the ring. The induced EMF causes eddy currents in the ring, and of course, the eddy currents in the ring dissipate thermal energy. The eddy currents in the ring dissipate thermal energy. So note that the thermal energy has been derived from the oscillations of the ring. So the thermal energy comes from the energy of oscillations. The thermal energy comes from energy of oscillations. That's why it is now having fewer oscillations before it comes to rest. The energy of oscillations is being dissipated as thermal energy due to eddy currents which have been generated in the ring. Alternatively, we can explain this in terms of Lenz's law. Starting from eddy currents, we can say the eddy currents in the ring also cause the magnetic field around the ring, which causes an opposing force in accordance with Lenz's law. So instead of talking about the dissipation of energy, I can simply say that the eddy currents or the currents in the ring also causes magnetic field around the ring, which causes an opposing force that is in accordance with Lenz's law. So that means the opposing force causes the oscillations to die out. That is, if the eddy currents cause a magnetic field creating a force in the opposing direction of motion, that means the oscillations must die out. But of course, the easiest one is to explain in terms of dissipation of energy of the oscillations. Dissipation of energy of the oscillations. The ring in B is now cut so that it has the shape shown here. So you see a certain part has been removed. What does that mean? We have reduced the magnetic flux linkage. We have also reduced the eddy currents. Explaining why when the procedure in B is repeated, the cut ring completes more oscillations. We have actually reduced the eddy currents. We even don't have a continuous flow of these currents. Okay. So the question is, explain why when the procedure in B is repeated, the cut ring completes more oscillations. So we can see that current cannot pass all the way around the disk or around the ring because we have cut some piece off. So cannot current cannot pass all the way around the disk. Not around the disk, around the ring. So it means the induced eddy currents are smaller. The induced eddy currents are smaller, and if the eddy currents are smaller, it means the rate of dissipation of energy is also smaller. So the rate, so we have a smaller rate of dissipation, of energy. So more oscillations occur. Because there's a smaller rate of dissipation of energy, more oscillations occur. Alternatively, you can explain this in terms of Lenz's law. There will be smaller resistive force, so more oscillations. So instead of talking about a smaller rate of dissipation of energy, you would say there will be smaller resistive force. Smaller resistive force, so more oscillations. Okay, as simple as that. Next, explain what is meant by a magnetic field. We have seen a magnetic field is a region of space where a magnetic pole experiences a force or causes a force. A region of space where a magnetic pole, let me just use a magnetic pole or a magnet. It can be a moving charge. It can be a magnetic material. It can be a current carrying wire. Current carrying conductor experiences or causes a force. Experiences a force or causes a force. That is a magnetic field. A region of space where a current carrying wire or conductor experiences a force or causes a force. A region of space where a magnetic pole causes or experiences a force. That is a magnetic field. The apparatus shown, the figure, is used to in an experiment to find the magnetic flux density B between the poles of a horseshoe magnet. Assume the magnetic field is uniform between the poles of the magnet and zero elsewhere. So we have that. The rigged metal rod of length 300 millimeters is fixed in position perpendicular to the direction of the magnetic field. The poles of the magnet are both 45 millimeters. So it means the length of this conductor, which is in the field, must be 45 millimeters approximately. There is a current in the rod that causes a force on the rod. The balance is used to determine the magnitude of the force. The variation with current I of the force F on the rod is shown here, and you see it is a straight line. So we have a straight line here. I can try to minimize this. So we have a straight line, force with current. Calculate the magnetic flux density B. So we want to calculate the magnetic flux density. So first of all, the force on the conductor is given by Bill. Because the conductor is at 90 degrees, we shall ignore the sine theta. So that is Bill. So the magnetic flux density is going to be the force, which is 9 times 10 power, let me see, the maximum force here is 9, that is 9 times 10 power negative 3. 9 times 10 power negative 3 divide by I, which I is current. The current is 5 from here. The current is 5 times 10 power, no, it is just 5 amperes. The current is 5 amperes, then times the length of the wire in the magnetic field is only 45 because the poles have a length of 45. It means only 45 millimeters of the wire is in the magnetic field, even though the wire is 300 millimeters. So L is going to be 45, not 300. So this will be 45 times 10 power negative 3. And I press my calculator. So this is 5 times 10 times 45 times 10 power negative 3. So this is giving me 0.040 Teslas. Okay. In a different experiment, electrons are accelerated through a potential difference and then enter a region of magnetic field. The magnetic field is into the plane of the paper and is perpendicular to the direction of travel of the electrons. Explain why the electrons follow a circular path when inside the region of the magnetic field. We have answered this question several times, so we shall just answer it. The magnetic force is constant. Magnetic force is constant. It's constant and always normal to the direction of motion. And always normal to the direction of motion or direction of velocity. The force does not change the speed. Because it is always normal, the force does not change the speed. It does not change kinetic energy. It does not change, it means no what? No work done. There is no work done by the force because it cannot change speed. It cannot change kinetic energy. So there is no work done by the force. So we simply say that the magnetic force just provides the centripetal force. The magnetic force just provides. The magnetic force just provides the centripetal force. The magnetic force just provides the centripetal force. As simple as that. State the measurements needed in order to determine the charge to mass ratio E over m of an electron. So we look at the formula. The magnetic force provides centripetal force BQV is equal to mv squared over r. So you want to find the charge to mass ratio. So Q over m is equal to V. That is V. One V has cancelled. That will be V over B times R. So first of all, you may need the magnetic flux density. magnetic flux density. You may need the magnetic flux density. You may need the radius of the path. You may need the radius of the path of the semicircle. You may also need, because the speed v is depending on the accelerating PD, so you may also need the accelerating PD. You may need the accelerating PD because the speed v is depending on the accelerating PD, because kinetic energy Ek is equal to half mv squared, and kinetic energy is charge times accelerating PD. Those are some of the quantities. You also note that if we were to find momentum, the momentum could also help you. We know that momentum is equal to B QR, which is the same as the square root of 2m times V times Q. So it means this can also help us to find the charge to mass ratio, so we may need the accelerating field in that case. Okay. Next, a slice of a conducting material has its face QRLK normal to a uniform magnetic field of flux density P, as illustrated here. So we are seeing this flux density B, direction of movement of electrons is coming from this side, and the flux density is horizontal from the other side. Okay. Electrons enter the slice traveling perpendicular to face PQKJ. For the free electrons moving in the slice, state the direction of the force on an electron due to movement of the electron in the magnetic field. So we pull out Fleming's left-hand rule. The first finger must point in the direction of the field, that is towards that side, that is towards your left. Then instead of the second finger pointing upwards, in the direction of the electrons, you reverse it so that it points in the opposite direction to where the electrons are coming from. By doing that, you are noticing that the thumb is pointing onto the table. Making the second finger to point in this direction, you rotate your hand through 180 degrees. If the first finger was pointing, the second finger was pointing in that direction, and the first finger was pointing in that direction, when you rotate the second finger through 180 degrees to point in the opposite direction, so that it now points in the opposite direction, that of the electrons, the thumb is pointing onto the table. So the thumb is pointing onto the table. That means the electrons move downwards. State the direction of the force on the electron, so the force is downwards. That is, the force is downwards, or it is towards the plane MLKJ, downwards. Okay. Identify the faces using the letters on the figure between which a potential difference is developed. So because the electrons are experiencing a force which is pushing them to the bottom part, the positive ions will be pushed towards the top part. So it means it is between Q, R, S and J, K, L, M. The electrons move towards this face. The positive ions move towards the top face. Explain why the potential difference in A reaches a maximum value. In other words, why doesn't the PD grow indefinitely? That's what we are talking about here. Okay, so first of all, as electrons accumulate on one side, the positive ions on the other side, this creates an electric field, which creates a force that opposes the force due to the magnetic field. When these two forces balance, then no more accumulation of electrons occurs, so the potential stops growing. So we say as charges separate, as charge separates, let me just use a single word, as charge separates, an electric field is created. An electric field is created between opposite faces. Maximum value of PD is reached when the electric force on the electron is equal and opposite to the magnetic force. Maximum value of PD is reached when the electric force, that is the force due to the electric field, maximum value of PD is reached when the electric force is equal and opposite. Is equal and opposite to the magnetic force on the electron. So the potential reaches a maximum value when the PD, which is created an electric force that is equal in magnitude but opposite to the magnetic force on the electron. When they are balancing, the PD stops growing. The number of free electrons per unit volume, that is N, in the slice of the material is given as 1.3 times 10 power 29 per meter cubed. The thickness PQ is given as 0.1 millimeters. The magnetic flux density is given as 4.6 exponent negative 3. Calculate the potential difference across the slice for a current of 6.3. So we know that whole voltage VH is equal to B times I over NTQ. This expression is not always given, so you need to know how to arrive at it always. So B is 4.6 times 10 power negative 3. The current is 6.3 times 10 power negative 4. Number is 1.3 times 10 power 29. Thickness is 0.10 times 10 power negative 3 to change it to meters. Then the charge, because they are electrons, we shall use 1.6 times 10 power negative 19. Back to my calculator. 4.6 times 6.3 divided by 1.3 exponent 29 divided by 0.1 exponent negative 3 divided by 1.6 exponent negative 19. So my calculator is giving me 1.4 times 10 power negative 12 volts. I hope I pressed it correctly. Yes. Let me press it again. 4.6 negative 3 times 6.3 exponent negative 4 divided by 1.3 exponent 29 divided by 0.1 exponent negative 3 divided by 1.6 exponent negative 19. Yes, 1.4 times 10 power negative 12. The slicing scene is a metal. By reference, your answer suggests why hollow probes are usually made using semiconductors. See the PD. So they are saying the slice is a metal. So this value of PD is too small to be measured. But then if we use a semiconductor, we know that for a semiconductor, For semiconductors, we know that n is much smaller. So VH is much larger. VH is much larger and more easily measured. VH is much larger and more easily measured for a semiconductor. Rather than getting such a value, a semiconductor has N which is much smaller, giving a large value of VH that is easy to measure. So that is the question there. Define magnetic flux. Of course, magnetic flux is just BA, where A is the area normal to the magnetic field. If you don't want to state that, you can say magnetic flux, the product of flux density, and the area normal to the magnetic flux, and the area normal to the magnetic field or magnetic flux. Alternatively, you can say magnetic flux is equal to BA sine theta, and you define all these symbols, where B is magnetic flux density, A is the area through which flux passes, area through which the flux passes, and then theta is the angle between the field and the area, or on the plane of the area. The angle between the field or the flux direction and the plane of the area, the angle between the field direction and the plane of the area. Okay, but the easiest is that one, product of flux density and the area normal to the magnetic field, that is magnetic flux. A simple transformer consists of two coils of wire wound on a soft iron core, as illustrated here. There is a sinusoidal current in the primary. Explain how this current gives rise to an induced EMF in the secondary. How does the current in the primary give rise to an induced EMF in the secondary? The current is alternating. There's a sinusoidal current in the primary, so it is alternating. So I'll simply say, we know that when alternating current in the primary flows, it creates a magnetic field in the core. The magnetic field is linked with the secondary. When the magnetic field cuts the coil of the secondary, an EMF is induced in accordance with Faraday's law. So we are going to say that alternating current SC in the primary creates a changing magnetic field or magnetic flux. Creates a changing magnetic flux in the core. Note that the core links the secondary. The core links the magnetic flux with the secondary. The core links the magnetic flux with the secondary coil. The core links the magnetic flux with the secondary coil, and by Faraday's law, And by Faraday's law, the changing flux linked with the secondary causes an induced EMF in the secondary. By Faraday's law, the changing flux in the secondary or around the secondary causes an induced EMF. In the secondary. So that's why the current in the primary is giving rise to an EMF in the secondary. Explain why the EMF induced in the secondary is not constant. Explain why the EMF induced in the secondary is not constant. Of course, according to Faraday's law, the rate of change of magnetic flux is directly proportional to the induced EMF. Therefore, because we are using alternating current, the rate of change of flux is not constant. So the induced EMF cannot be constant. So we are saying the rate of change of flux is not constant. The rate of change of flux is not constant, and by Faraday's law. And by Faraday's law, the induced EMF is proportional. The magnitude, remember, is proportional to this rate. Is proportional to the rate of change of flux. So, not constant. Because the rate of change of flux is not constant, and yet by Faraday's law, the induced EMF is proportional to this rate, is proportional to the rate of change of flux, so it can't be constant. Okay, explain why the soft iron core is laminated. We now know the purpose of laminating. We shall see this many times in the next unit of SC. Why is the core laminated? So we know that laminating reduces the induced eddy currents from becoming larger. Hence, this reduces energy losses in the core due to the eddy currents. So laminating reduces induced eddy currents in the core, reduces induced eddy currents in the core, hence reduces energy losses in the core due to eddy currents. Laminating prevents eddy currents from growing up or from adding up to become larger to cause a larger effect. So it reduces energy losses in the core due to eddy currents. That is the purpose of laminating. It reduces eddy currents from growing larger, which reduces energy losses due to eddy currents. Okay. Next, a small coil is placed close to one end of a solenoid connected to the power supply. The plane of the small coil is normal to the axis of the solenoid as illustrated here. So it means the magnetic field from this solenoid is actually at 90 degrees to the plane of the coil or to the area of the coil. The power supply change causes the current I in the solenoid to vary with time t as shown here. State Faraday's law. Of course, we now know Faraday's law, the magnitude of the induced EMF. The magnitude of induced EMF is directly proportional to the rate of change of magnetic flux linkage. That is Faraday's law. The magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. On the axis of the figure 9.3, sketch a graph to show the variation with the time t of the electromotive force induced in the small coil. We want to draw the graph of E against time. Let's go back to the graph first. So here we have zero current. We know that the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. When the current is zero, it means, and is zero and constant, not changing, it means the exchange of flux is zero. So EMF induced is going to be zero. Whenever the current is constant, like at this point here, between this point here and in the middle here, somewhere here before we reach T2, the current is constant. So it means it is not changing. So the rate of change of flux linkage is zero because the current is not changing. The magnetic flux linkage is constant. Therefore, between t equals to this point here and t equals to this point here is again the current is constant. So the EMF is zero. So here it is zero. Here the EMF is zero. And after that it is also zero. So the EMF is just changing at this point here where there is a change. These are two small boxes. So this is two small boxes, and this one is in one small box because it starts from the center here up to the center here, so it is one small box. So the gradient here is twice the gradient here. Therefore, it means the EMF represented by around T2 should be twice the EMF represented by T1. The gradient is constant because they are straight lines, so the EMF is constant, very close to T1 and very close to T2. The gradient here is positive, the gradient here is negative, so the EMFs are in opposite directions. They have opposite polarities. So if I say the EMF here is positive, the EMF there will be negative. If the EMF here is represented by 5 boxes, the EMF here will be represented by, actually if here it is 10 boxes, here it will be 5 because the gradient here is a half of the gradient the other side. Therefore, on our graph, we now sketch our graph. Close to one box close to T1, the EMF only changes here, and between T2 in the center of this box here and this one here, the EMF changes here. Elsewhere, the EMF is zero. So I'm just going to draw a horizontal line. I hope I get my ruler. We have seen that when the current is constant, the EMF is zero. And current is constant before T1 and it is zero. So we have a horizontal line. Current was also constant after T2. So we shall have another horizontal line here. Then current was constant between T1 and T2 because although it was not zero, the current was not changing. So we shall have another horizontal line here. So there's just a change at those 2 points, as shown by the graphs of current. So we are going to represent, because the first gradient was half of the second gradient from here. The first gradient, you see the the vertical change is the same, but here the first gradient is represented, the x-axis is 2 boxes, yet here it is 1 box because it starts from the center of this box and the center of the next box, so it is 1 small box. So it means the gradient for around T2 is twice the gradient around T1. I'm going to represent the first by 10 small squares. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm representing this by 10 small squares. I'll represent the other one by 20 small squares. So here I have 20 small squares. I think I reach the other extreme end. Note that this is in the center of those 2 boxes. So now you draw your vertical lines to make these steps look nice. This one is in the center of this box. It's only that I don't have, I'm using a pen, not a ruler, but at least I'm trying. Okay, this other one is supposed to be narrow. People will think it is, maybe the second line is over exaggerated. I want this line to be just in the center of the box because it is supposed to be very narrow. Yes, just like that. So that is how we're going to represent this current. Of course, we're using a ruler. You can draw a very neat diagram better than mine. Using your ruler, you can draw a very neat diagram better than mine. So that will be the graph for the induced EMF. Note the magnitudes at T2 and T1. The magnitude at T2 is twice that at T1 because of the gradients. Second, you saw that the gradients were in opposite directions, so that meant different polarities of induced EMFs. Note that the EMFs are constant because the gradients were constant. Note that whenever the current remained constant, the EMF was 0. As simple as that. Okay, next. The small coil in A is now replaced by a Hall probe. Of course, the Hall probe is going to give us either B or VH. The Hall probe is positioned so that the reading for the probe is maximum. So the Hall probe is positioned so that the reading of the probe is maximum. The current I in the solenoid varies again as shown in the figure 9.2. The current was shown by this figure here, 9.2. Of course, now we are dealing with the voltage. I will rub off this so that I deal with the voltage. Recall from magnetic fields that the whole voltage VH is equal to BI divided by NTQ. Now it is the current which is varying. It is now the current that is varying. And if the current is varying, therefore, and we see that VH is directly proportional. VH is directly proportional to I. If B is constant, VH is directly proportional to I. What does this imply? It means that the graph of VH against time is going to be exactly the same as that of current with time because VH is directly proportional to I. So we just draw a replica of the same graph. We shall just do a replica of the same graph. When current is 0, VH is 0. When current is maximum, VH is maximum. When current is increasing, VH is increasing. As simple as that. Therefore, in our graph, we just look for the time. Current was only changing between T1 around here and here, and it was changing in between these boxes, here and here. So we shall just draw a direct replica of the same current. Although it was represented by how many boxes? We shall just represent it with any value, there is no problem. So when the current is constant and 0, the voltage is constant and zero. So that is a horizontal line along the x-axis. So even here, it will be a horizontal line along the x-axis. When the current is constant, the whole voltage is also constant, because we have seen that VH is equal to BI divided by NTQ. They're directly proportional. So we draw a horizontal line elsewhere in the middle of the T1 and T2 to represent a constant voltage. I will choose at this point here. This should be in the middle, somewhere here. So here I will draw another horizontal line because VH is constant but not zero. Then, of course, I told you as the current increases, VH also must increase. So I will draw another line here which is exactly similar to that of current. And I will draw another line here, exactly similar to that of current. It is in the center of the box for you because you are using a ruler. I made it thick so that it is very visible. You can draw a better one. So that is the graph of against VH against time. That is the graph of VH against time. Okay. So let's see the next question. So a long straight vertical wire A carries a current in an upward direction as shown there. The wire passes through the center of a horizontal cardboard as shown there. So that is the diagram. The card is viewed from above. The card is shown from above and is here. So look at the card and try to use your right hand and see the direction of the magnetic field first. You must have noticed from the right hand grip rule that actually the field lines are going to be concentric circles since it is due to a current carrying wire, but these must be anti-clockwise. So when we draw concentric circles, here you can use a compass. To draw extremely neat concentric circles, you can use a compass placed at the center of the wire. And remember, the field lines must increase in separation as we move away from the wire. So I'll draw concentric circles. Me, I'm using a free hand. So for you should use a compass to draw neat concentric circles. Their separation increases as you move away from the wire. Okay. So the question was draw 4 lines. I think I drew 4 to represent the magnitude, the magnetic field. By the right hand grip rule, the field lines are going to be in an anti-clockwise direction. I am saying you must draw using a compass to make this to look extremely neat and equally well drawn, so that there is no any confusion. Okay. Next, two wires A and B are now placed through a card. The two wires are parallel and carrying currents in the same direction as shown here. So these are carrying currents in the same direction as shown here. They are carrying current in the same direction as shown here. Explain why a magnetic force is exerted on each wire. Of course, each wire is in the magnetic field of another wire, and therefore must experience a force because the magnetic field of each is at right angles to the other conductor. And when a conductor is in a uniform magnetic field, it is carrying current normal to the magnetic field, it must experience a force. Therefore, the current in each wire creates a magnetic field. The current in each wire creates a magnetic field. The current in each wire creates a magnetic field at the other wire. In other words, the other wire, each wire is in the magnetic field of the other because the current in each wire creates a magnetic field. The current in the wire is going to be at 90 degrees because if you remember, we always drew a tangent in the plane. That is, if we were to draw a tangent in the plane of the field, the horizontal plane would be like away from you. So current in the wire is at 90 degrees to the field. The current in the wire is at 90 degrees to the field. The current in the wire is at 90 degrees to the field, and by Fleming's left-hand rule, this causes a force. By Fleming's left-hand rule, this causes a force. So because the current in each wire creates a magnetic field at the other wire, the current in the wire is at 90 degrees. Of course, since the current in the wire is at 90 degrees to the field, by Fleming's left-hand rule, this is going to cause a force. For each wire, if we were to look at them from one plane, it would be very easy. If this is the position of one wire and the other is the position of another wire, they are all carrying current out of the page. If we draw a magnetic field pattern due to the first wire, then if this is anti-clockwise, then it is a tangent to this wire here. This is carrying current out of the page. First finger out of the page, first finger in the direction of the field, as second finger out of the page. You notice that there is a force on this one by Fleming's left-hand rule, which is attractive. State the direction of the forces. Of course, the force on each wire is towards the other wire, so the force is attractive. The force is attractive. We can say force on each wire the force on each wire is towards the other wire. The force on each wire is towards the other wire. Then part C, the currents in the two wires are not equal. Explain whether the magnetic forces on the two wires are equal in magnitude. Of course, whether the currents are equal or not, the magnetic forces are going to be equal because by Newton's third law, the forces are going to be equal but opposite, even though the force is directly proportional to the product of both currents. So the forces are going to be equal. So we are saying the force is proportional. The force is proportional to the product of both currents. So the forces are equal. Whether one current is larger than the other, the force is directly proportional to the product of both currents. Alternatively, you can remember Newton's third law. So by Newton's third law, I'll just write N3, that's Newton's third law. The forces are equal. The forces are equal but opposite. The forces are equal but opposite. So just say yes. According to the question, whether the forces are equal. So yes, they are equal because by Newton's third law, the forces are equal but opposite. They're just opposite. Okay, define the Tesla. Define the Tesla, 3 marks. The Tesla is a unit of magnetic flux density. It is a unit of magnetic flux density of a field normal to a long straight conductor carrying a current of 1 ampere, causing a force of 1 Newton per meter of its length. That is a unit of magnetic flux density. Of a field normal to a straight long conductor carrying a current of 1 ampere, causing a force of 1 Newton per meter of its length. That is a Tesla. So we say the magnetic flux density is 1 Tesla when a long straight conductor carrying a current of 1 ampere experiences a force of 1 Newton per meter of its length. That is a Tesla. We say the magnetic flux density is 1 Tesla when a long straight conductor carrying a current of 1 ampere normal to the uniform magnetic field experiences a force of 1 Newton per meter of its length. That is a Tesla. So when you're defining a Tesla, you just need to think about the magnetic flux density being perpendicular to the current. Think about the force, Newton per ampere, and Newton per meter. That is a Tesla. Okay, next. A magnet produces a uniform magnetic field of flux density B in the space between the poles. A rigid copper wire carrying a current is balanced on a pivot. Part PQLM of the wire is between the poles of the magnet as illustrated here. See the illustration. The wire is balanced horizontally by means of a small weight W. So there is a small weight here. So this one is causing, of course, it will cause clockwise, anti-clockwise moments. If there is a force on the wire, then it will cause, so this one is causing clockwise moments. This would cause anti-clockwise moments. The section of the wire between the poles of the magnet is shown here. So we see the section of the wire between the poles of the magnet. Explain why section QL of the wire gives rise to a moment about the pivot. Why does section QL give rise to a moment? So the current through QL is, I think, in that direction. PQ is downwards, LM is upwards. Of course, this section of the wire is in the magnetic field, and the magnetic field is normal to it. Therefore, by Fleming's left-hand rule, the field is from north to south. The first finger points in that direction. The second finger is pointing from Q to L. So the second finger points from Q to L. There is a force downwards. There's a force on this one downwards by Fleming's left-hand rule. So they said explain why section QL of the wire gives rise to a moment about the pivot. So we have seen that wire QL is perpendicular to the magnetic field. Wire QL, or I'll just say QL, is perpendicular. QL is perpendicular to the magnetic field. QL is perpendicular to the magnetic field. So current in the wire QL gives rise to a vertical force. Gives rise to a vertical force which does not act through the pivot. So taking you back to the diagram, there is a current flowing through QL in that direction and the field is in that direction. So the field is at 90 degrees to the wire. By Fleming's left-hand rule, the force is vertical downwards. So the force is acting vertical downwards. Yet, taking you back to the previous diagram, if the force is acting in the vertical plane, then it causes a moment above the turning point. The force does not act through the pivot. Therefore, it causes a moment. So QL is perpendicular to the magnetic field, so current in the wire QL gives rise to a vertical force, which does not act through the pivot, thereby causing a moment. Okay, so causing a moment. So it causes a moment. Section PQ and LM of the wire do not affect the equilibrium of the wire. Explain why. PQ and LM do not affect the equilibrium of the wire. The current here is vertically downwards. The current in LM is vertically upwards. Still there are forces, by the way. By Fleming's left-hand rule, the first finger points from north to south. By Fleming's left-hand rule, the first finger points from north to south. Note that the current in PQ is downwards. The current in the PQ is downwards, so the second finger points downwards. First finger from north to south, second finger downwards. So when you make the second finger downwards, it means you notice that the first finger, the thumb is pointing towards you. It is in a horizontal plane towards you. Similarly, when you check LM, the first finger is pointing from north to south. The second finger must point upwards. The thumb points into the page. So the first one is pointing towards you, that is out of the page. The second one is pointing into the page. So the forces are in a horizontal plane. The forces are in the horizontal plane, therefore there is no way they can cause moment, so they do not affect equilibrium. So the forces and by the way, the forces are in opposite directions and they will be equal in magnitude. So we are saying the forces are horizontal. The forces are horizontal and act through the same line. And act through the same line. The forces are horizontal and act through the same line. These forces are equal in magnitude and in opposite directions. These forces are equal in magnitude and opposite in direction. So you can even say cancel out. So they cancel out, or their effect cancels out. Even though since they're in the horizontal plane, their effect does not affect equilibrium. Okay, then section QL of the wire has length 0.85 centimeters. Section QL. So this part here, QL, has a length of 0.85 centimeters in the magnetic field. Or maybe I go back here. Okay, it has 0.85 centimeters in the magnetic field. The perpendicular distance of QL is 5.6 from the pivot. When the current in the wire is 1.2 amperes, W is moved a distance 2.6 centimeters along the wire in order to restore equilibrium. Note that for equilibrium, the moments, the clockwise and anticlockwise moments must be equal. W is given as 1.3 times 10 power negative 4 kilograms. Show that the change in moment of W about the pivot is given by that. So we want to see the change in moment. We shall go back to the diagram here. We shall go to the first diagram here. So they have given us the distance, the length of QL. We have seen that QL is causing a vertical force downwards. And remember, the force due to the magnetic field is given by B. And they are saying the perpendicular distance of QL from the pivot is 5.6. So they have showed us 5.6 here, perpendicular distance. And they told us that when the current flowing is 1.2 amperes, the distance which W should be moved to the pivot, this distance should be 2.6 centimeters for equilibrium to be restored. So we want to find the change in moment of W about the pivot. Change in moment. Of course, the force caused by this one is its weight, it is mg. So the moment caused by this change in distance or change in length is going to be the weight times the perpendicular distance of that weight from the pivot, which I'm calling delta L. Okay, so the change in moment, because moment is the product of force times perpendicular distance, the change in moment is going to be equal to the weight, which is m times g times the change in length or the distance through which it is moved. They've given us the mass as the mass is 1.3 times 10 power negative 4, g is 9.81, and the change in length is 26 centimeters, which is 2.6 centimeters, which is 2.6 times 10 power negative 2. I just check with my calculator. 1.3 times 9.81 times 2.6 So this is giving me 3.31 times 10 power negative 5, which is approximately the same as that. Use the information in Roman 1 to determine the magnetic flux density B between the poles of the magnet. So remember, equilibrium is being restored. So it means, and remember the force caused by the force on the wire is given by Bill. The force here is going to be given by Bill. The force here is going to be given by Bill, where L is going to be the length of the wire in the magnetic field. Then we multiply this by the perpendicular distance, which is 5.6. That is the moment caused by this force. So that will be Bill times the distance from the pivot. For equilibrium, this should be equal to the other moment, which we have said is W times perpendicular distance delta L. So we just substitute these two. We just say that the force or the change in a moment that we have obtained above should be balanced by the force, which is B times the perpendicular distance x. So this is going to be equal to 3.3 times 10 power negative 5 should be equal to B times the current, which is 1.2. The length of the wire in the magnetic field was 0.85, so it is 0.85 times 10 power negative 2 to change it to meters. Then times the distance was 5.6 from the pivot, which is 5.6 times 10 power negative 2. So we now substitute. We press the calculator and divide. So I just divide by 1.2, 0.85, 5.6. And this is 5.8 times 10 power negative 2, or 0.058 Teslas. So that will be the magnetic flux density between the poles of the magnet. Number 9. A coil of wire is situated in a uniform magnetic field of flux density B. The coil has diameter 3.6 and consists of 350 turns. Diameter is 3.6, number of turns is 350. Okay. The variation with the time t of B is shown in the figure. Show that for the time t equals to 0 to time t equals 0.2, the EMF induced is 0.08. So EMF induced is equal to the rate of change of magnetic flux linkage, that is BAN, or NBA. So the magnetic flux is actually, is it 40? So this is in the center here. So 41, it is halfway, so it is 45. So that is going to be 45 milliteslas, 45 times 10 power negative 3. They gave us number of turns was 350. They gave us the radius as 3.6. The diameter was 3.6. The radius is 1.8. So this is going to be times pi r squared, that is 1.8 times 10 power negative 2 squared. Then divide by the time between 0 and 0.2. The time is 0.2. So I press my calculator. So from my calculator, I've just checked and I've seen that is approximately 0.080 volts to two significant figures. So it is approximately that. Then on the axis of the figure, 9.3 show that the variation with the time t of the induced EMF E for the time t equals to 0 to time t equals to 0.80 seconds. So we are going to show the variation of E with time. Note that E is directly proportional to the rate of change of magnetic flux linkage. there should be a change in magnetic flux linkage. They gave us a graph of B against time, and it means E is the rate of change is directly proportional to B. If B is constant, the change in flux is 0. If B changes, then the magnetic flux also is changed. The rate of change is also good. There is a change in flux linkage. But you notice, so it means E is going to be directly proportional to the gradient of B against T, of B against T. At points where the gradient is 0, EMF induced is going to be 0. So between T equals to 0.2 to 0.2, around here, EMF is going to be 0. Then here the EMF must be constant because the gradient here is constant. And here the EMF is constant because the gradient is constant. However, let's check how the gradients are varying. For the first part, we saw that the EMF was 0.080. And this was correspond to a gradient, which is, you notice that here the change in the vertical is the same, only the change in the x is different. So here you see the change in x is twice the change in x here. That means the EMF correspond to this part was 0.08. Therefore, this one should be half of this. This should be 0.04. Therefore, on your graph, you should take that into account. So we have seen for 0.0 to 0.2, the EMF was 0.08. So we should sketch that. 0.01, 02, 03, 04, 05, 06, 07, 08 is around here. So 08 is around here. And this is a constant, so this is going to be a horizontal line. Let me increase the thickness. So this is a horizontal line. Then between 0.2 to 0.4, we saw that the B was constant, the EMF is 0, so we draw a horizontal line along the x-axis. Then again, between 0.4 to 0.6, B was decreasing. It was actually, the gradient was in the opposite direction, but we saw that the gradient was a half of the first gradient, so the EMF is a half of the first one. Therefore, since we have represented this as with 8 small squares, this should be with 4 small squares, 1, 2, 3, 4. So this should be along this point here. It should be along that point. So I will just join these with vertical lines so that I come up with such a graph. So that is the graph. That is the graph. Note that E is now depending on B, is directly proportional to B. If B does not change, then E will not change. I mean, E will be 0. If B changes, E will be a constant value because it is depending on the rate of change. E is depending on the rate of change. If E changes in the direction, if B changes in the opposite direction, then E will also have an opposite polarity. That's why we are arriving at such a graph. Okay. Next. A bar magnet is held in a small distance above the surface of an aluminum disc by means of a rod as illustrated here. The aluminum disc is supported horizontally and held stationary. The magnet is rotated about a vertical axis at a constant speed. Use the laws of electromagnetic induction to explain why there is a torque acting on the aluminum disc. What is torque? You should be now thinking, what is a torque? What is a torque? So when in regards to the laws of electromagnetic induction, we shall be referring to Lenz's law and Faraday's law. So the aluminum disc is supported horizontally and held stationary. The magnet is rotated. There is movement. So when we see that there is a movement, there is cutting of flux lines. So we say the disc cuts flux lines. The disc cuts flux lines. The disk cuts flux lines of the magnet because the disk cuts flux lines of the magnet. There is a changing flux in the disk. There is a changing flux in the disk. There's a changing flux in the disk. And by Faraday's law, if there is a changing flux in the disk, then an EMF is going to be induced. So by Faraday's law, an EMF is induced. An EMF is induced in the disk. An EMF is induced in the disk. Of course, this EMF is going to cause again eddy currents. By Faraday's law, an EMF is induced in the disk. The EMF causes eddy currents. The EMF causes eddy currents in the disk. Again, the eddy currents are going to cause another magnetic field. The current is in the magnetic field of the magnet and therefore causes a force on the disk. The current is in the magnetic field. The current is in the magnetic field of the magnet and therefore causes force. The current is in the magnetic field of the magnet and therefore causes force on the disk. Thus, a torque acts on the disk. Of course, when we talk about a torque, we are referring to a moment. Thus, a torque acts on the disk. So imagine before the movement of the magnet, there was no current in the aluminium disk. But when the magnet moves, the disk cuts the flux lines of the magnet, so there is a changing magnetic flux in the disk. And by Faraday's law, an EMF is induced in the disk. The EMF is causing a current. Now there is a current again in the magnetic field of the magnet. Therefore, if there is a current in another magnetic field, the conductor which is carrying the current must experience a force. That's why the disk experiences a torque. Thus, there will be a torque. Thus, a torque acts on the disk. Okay. Next. An electron traveling at a speed v in a straight line in a vacuum, it enters a uniform magnetic field of flux density given as this one. Initially, the electron is traveling at right angles to the magnetic field as illustrated. The path of the electron in the magnetic field is an arc of a circle of radius 6.4 centimeters. State and explain the direction of the magnetic field. So let's come back here. First of all, the path of the electron is showing that the force is downwards because the path is downwards. So the force due to the magnetic field is going to be in that direction. So the second finger which shows, the thumb which shows the force should point downwards. And the second finger, which shows direction of the particle, must be the opposite direction to that of the electron. Therefore, if we make the thumb to point towards you or downwards, because the bottom of the page is next to you, the thumb is pointing towards you. In trying to rotate the hand so that the second finger points away from you, points to the left, you're going to realize that actually the field must be into the plane of the page. The thumb trying to point towards you, with the second finger pointing to the left, the first finger is pointing downwards, that is to the page. So we say that the field is into the page by Fleming's left-hand rule. So we are saying the force is downwards, the force is downwards or down the page. The force is down the page. The force is down the page. And the current is from left. Of course, if the electrons are moving from left to right, the current is from right to left. So the current is from right to left because current flows in the opposite direction to that of the electrons. By Fleming's left-hand rule, the field is into the plane of the page, or into the plane of the paper. So the force is down the page, the current is from right to left. In other words, if electrons are moving from left to right, the current must be in the opposite direction. You could also use the right hand directly. You make the first, of course, when you use the right hand, you must be an expert. You don't reverse the second finger. You keep it in the same direction as the electrons, the thumb downwards. The thumb is down the page. The first finger will still be into the page. So the field is into the page. Show that the speed of v of the electron is 9.0 times 10 power 6 speed. So since the magnetic force provides the centripetal force for a particle in a magnetic field, so we are saying magnetic force provides the centripetal force. Magnetic force provides the centripetal force. Therefore, it means B QV should be equal to mv squared over r. Making V the subject, V is going to be, because one V cancels, V is going to be BQR over M. BQR over M, so we just substitute. So V is going to be B, which is, they told us B is 8.0 times 10 power negative 4 Teslas. So that is 8.0 times 10 power negative 4. The charge of an electron is 1.6 times 10 power negative 19. The radius is 6.4 centimeters, so this will be 6.4 times 10 power negative 12, negative 2, divided by m. It is an electron, 9.11 times 10 power negative 31. Pressing my calculator, 8 exponent negative 4, 1.6 exponent negative 19 times 6.4 exponent negative 2 divided by 9.11 exponent negative 31. So this is giving me exactly 9.0 times 10 power 6. 9.0 times 10 power 6 to two significant figures as the speed. A uniform electric field is now applied in the same region as the magnetic field. The electron passes undeviated. We have already seen that the magnetic force was downwards because the field was into the page. If the electric field is applied for the electron to pass undeviated, the force due to the electric field must be upwards. The force due to the electric field must be upwards. Note that an electron experiences a force in an electric field in the opposite direction to the field. So if the electron is experiencing a force upwards, it is because up is positive and bottom is negative. And electric field lines originate from high potential to low potential. Therefore, they said on the figure, mark with an arrow the direction of the uniform magnetic field. So since they said mark with an arrow, all this was just explanation so that people can know how we arrived at the answer. So I will just put there one arrow pointing downwards, and that is the electric field. Use data from A to calculate the magnitude of the electric field strength. Use data from A to calculate the magnitude of the electric field strength. Okay, so we saw that when the particles pass through undeviated, it is because the force due to the magnetic field is equal to the force due to the electric field. That is BQV is going to be Q times E. So V is going to be equal to, actually we want to find E. So it means E is going to be B times V. So since we have already found V and B was 8.0, so E is going to be 8.0 times 10 power negative 4 times the value of V, which we have got as 9.0 times 10 power 6. When you press your calculator, so this is 7.2 times 10 power 3. 7.2 times 10 power 3. The electron in B is now replaced by an alpha particle traveling at the same speed, v, along the same initial path. Same speed along the same initial path. We know that an alpha particle has mass 4u, it has charge twice e. Describe and explain the shape of the path in the region of the magnetic and the electric fields. The shape is going to be the same. The particle will pass through, the alpha particle will still pass through undeviated, simply because for the particle to pass through without being deviated, V depends on E over B. It does not depend on the mass or the charge of the particle. So we shall simply say undeviated or not deviated. It is still undeviated. Reason: the condition for deflection, condition for no deflection. Condition for no deflection depends only on V, on the speed, and does not depend on the mass of the particle or on the charge. So even though we have replaced the electron with the alpha particle, which has more mass and a bigger charge, the conditions for no deflection do not depend on the mass or the charge of the particle. Therefore, still there is no deflection. Undeviated condition for no deflection depends only on V and does not depend on M or Q. Okay. State Faraday's law. The magnitude of the induced EMF. Magnitude of induced EMF in, say, a coil is directly proportional to the rate of change of magnetic flux linkage. The magnitude of the induced EMF in a coil is directly proportional to the rate of change of magnetic flux linkage. A simple ion-cored transformer is illustrated here. What is the purpose of a transformer? What is the function of the transformer? The major function of a transformer is to transform, to change. What does it change? It changes the size of the voltage or the PD. That's why we have step up or step down. So the purpose is to change the magnitude. Change the magnitude of potential difference. To change the magnitude of the potential difference, or to step it up or step it down. A sinusoidal alternating current in the primary coil gives rise to a varying magnetic flux, linking the secondary coil. Use Faraday's law to explain why the output from the transformer is an EMF that is alternating. A sinusoidal alternating current in the primary coil gives rise to a varying magnetic flux linking the secondary. Use Faraday's law to explain why the output from the transformer is an EMF that is also alternating. Okay, so of course, we know how this is formed. The magnitude of the EMF varies as the rate of change of magnetic flux linkage according to Faraday's law. But then the direction of the EMF changes when the direction of change of flux also reverses. That is, when flux changes from, say, decreasing to increasing or increasing to decreasing, it means the direction of the EMF has changed. And therefore, the magnitude of the EMF should also be changing. And since flux is continuously increasing and decreasing because of the sinusoidal alternating current, then it means the polarities will also continuously switch from positive to negative and so on and so forth. Okay, so we are saying the magnitude of EMF varies as the rate of change of flux as the rate of change of flux changes. If the rate of the magnitude varies as the rate of change of flux changes. The direction of the EMF changes when the direction of change of flux reverses. When I talk about the direction of the EMF, I mean the direction of change of flux changing. I mean when flux changes from increasing to decreasing. Or it changes from decreasing to increasing. If the change in flux is increasing, or flux changes by increasing, then the EMF is induced in one particular direction. If flux now changes by decreasing, then the EMF must also change the direction. So since flux is continuously increasing and decreasing, because remember, alternating current has a magnitude which continuously increase and decrease before changing direction. So since flux is continuously increasing and decreasing, The polarity of EMF continuously switches. The polarity of the output EMF, of course, continuously polarity of output EMF continuously switches or changes. As simple as that. Then state why the soft iron core is laminated. I think that is now an easy question. We want to reduce energy loss due to the heating caused by eddy currents. To reduce energy loss or power loss due to heating of the core caused by eddy currents. We want to reduce energy or power loss due to heating of the core caused by eddy currents. Okay, next. A long straight vertical wire carries a current I. The wire passes through a horizontal cut EFGH as shown here. On the figure 8.2, draw the pattern of the magnetic field produced by the current carrying wire on the plane. So these are going to be concentric circles. This is out of the page. So you grip your pen in your right hand. The thumb points upwards because the current is out of the page. The fingers are folding anti-clockwise. So you draw concentric circles using a compass to make sure they are equally balanced, they are well balanced. Draw concentric circles whose separation increases as you move away from the wire. Make sure you draw concentric circles with the compass whose separation increases as you move away from the wire. Then by the right hand grip rule, the arrows are going to point in an anti-clockwise direction. Okay. Two long straight wires P and Q are straighted a distance 3.1 centimeters apart as illustrated here. The current in wire P is 6.2 and in wire Q is 8.5. The magnetic flux density B at a distance x from a long straight wire carrying current I is given by that expression. B is mu naught I over 2 pi x. Remember, mu naught was permeability of free space, and mu naught is 4 pi times 10 power negative 7, which is given in the list of constants. Calculate the magnetic flux density B, the magnetic flux density at wire P, at wire Q, due to the current in wire P. They told us that the magnetic flux density B at a distance x from a long straight wire carrying current is given by that expression. So we just substitute. The magnetic flux density B is going to be mu, which is 4 pi times 10 power negative 7. I said mu is permeability of free space, which is given in the list of constants. And I, we are looking at wire Q. The current in wire Q is, we want the magnetic flux density at wire Q due to current in wire P. So we are looking for current in wire P, which is 6.2. So this is 6.2 divided by 2 pi times the separation, which is the wires 3.1 centimeters apart. So this is going to be 3.1 times 10 power negative 2. I press my calculator very fast. Pi is cancelled. So this is giving me 4.0 times 10 power negative 5 Teslas. Calculate the force per unit length in newtons per meter acting on wire Q due to the current in wire P. So we want the force. Of course, the force is going to be given by Bill. Force is equal to BAIL. And we want the force per unit length. So it is F over L is going to be B times I, where B is 4.0 times 10 power negative 5. And remember, we want the force per unit length acting on wire Q. So we need the current in wire Q. And the current in wire Q was given as 8.5. So the other one is the magnetic field due to wire P. Then this is the force due to on wire Q. So this is going to be 8.5. Be careful when you are choosing which currents. Here we use 6.2. Here we are using 8.5. So be very careful. So the force per unit length is, I press my calculator, 4 times 8.5. So this is giving me 3.4 times 10 power negative 4 newtons per meter. The currents in wires P and Q are different in magnitude as we have seen. State and explain whether the force per unit length on the two wires will be different. Of course, the forces must be equal because the force per unit length is proportional to the product of the currents, and the product of the two currents is always the same, even though they have these different magnitudes. So we are saying the force per unit length is proportional to the product of the two currents. So same magnitude. So the forces have the same magnitude. Alternatively, you can think about Newton's third law. By Newton's third law, the forces are equal but opposite. By Newton's third law, the forces are equal but opposite. Next, electrons enter a rectangular slice P, Q, R, S, E, F, G, H of a semiconductor material at right angles to face P, Q, F, E, as shown here. A uniform magnetic field of flux density B is directed into the slice at right angles to the face P, Q, R, S. The electrons each have a charge negative Q and a drift speed V, as shown here. State the magnitude and direction of the force due to the magnetic field on each electron as it enters the slice. Let's look at the diagram very well. So state the magnitude and direction of the force due to the magnetic field on each electron as it enters. So you see that the magnetic field is going to be normal to the direction of the particles. The magnetic field is perpendicular to the direction of the particles because for it is coming from vertically upwards. The particles are just moving along the base. So the magnetic field is perpendicular to the direction of the particle. So it means the magnitude, instead of the force being equal to BQV sine theta is going to be 1. So the magnitude is going to be BQ V, that is the magnitude of the force. Then direction. The direction is going to be given by Fleming's left-hand rule. The direction, they didn't say to explain, they just want to state the direction. So by Fleming's left-hand rule, let's predict the direction. The first, if you hold your paper vertically, you raise your paper so that it is vertical. Make the first finger pointing vertically downwards along the paper. Instead of the second finger pointing that direction, you reverse it to point in the opposite direction. That is, you rotate it through 180 degrees. So you are going to notice that the thumb is going to point towards this side. The thumb is pointing towards QRGH. With the first finger pointing vertically downwards, instead of the second finger pointing in the direction of the electrons, you reverse it. You rotate your hand through 180 degrees. You notice that the thumb is pointing towards this. So the first finger is onto the table. The second finger is pointing towards you. When you rotate your hand, the second finger points towards you with the first one to the table. The thumb is pointing towards QRGH. Therefore, it means the direction will be given by either P to Q. You just use a letter which points towards QRGF. Or you can say E to F, which is the same direction. Or you could say H to G, it is pointing to that direction. Or you could say S to R. S to R. N of those can work. Not all of them, of course, N of those. We're just trying to show that the electrons move towards QRGF. Or you could simply say towards face QRGF. Okay, so that is the direction of the force. You can say towards the face GF. Towards the face QRGF. Okay. Next, the force on the electron causes a voltage VH to be established across the semiconductor slice given by that expression. I is the current, where I is the current. State the two faces between which the voltage is established. So if electrons are being pushed towards this end, the positive ion is towards the other end, so the voltages is developed between QRGF and PSHE. So the order of the letters does not matter. I can say PSHE and FGRQ. Those are the faces between which the whole voltage is developed. Use letters from the figure to identify T. T is the thickness, remember? T is the thickness, it can be QF, it can be PE, it can be RG, it can be SH. That is thickness, because Q is the thickness. So Q is the thickness, so we just use, because this is T, or it can be that one, N of those letters, so I will just choose N of those letters. You can say PE, you could say QF, you could say RG, you could say SH. You just want the thickness because it is the thickness. Aluminium 2713 has density of 2.7 grams per centimeters cubed. Assume that there is one free electron available to carry charge per atom of aluminium. Show that the number of charge carriers per unit volume is given by that. If you want to borrow expressions from ideal gases or from nuclear physics, you know that the number of nuclei, number of atoms over Avogadro's number is the same as the mass over the molar mass. And remember here, the mass is going to be the density times the volume. So it means you can think of the number of these particles or the number of atoms as being equal to the density times volume over the molar mass times Avogadro's number. So, since we want the number of charge carriers per unit volume, where volume is going to be 1 meter cubed, so we must change the density into meters, into kilograms per meters cubed. Alternatively, we can simply substitute here. Because the volume is 1 meter cubed, I will change the density into kilogram per meters cubed. So this is going to give me 2.7. To change it to kilograms, to be times 10 power negative 3. To change this one to to change it to per meter cubed, I think this will be times 10 power. Let me see. Okay, I just change this to kilograms per meters cubed. It will be times 1000. So this becomes 2700 kilograms per meters cubed, I guess. So let me just use directive values so that converting is now easy. So I'm changing this one to kilograms per meters cubed. I just multiply by 1000. So density will be 2700. The volume will be 1 meter cubed. This is kilograms per meters cubed. Kilograms per meters cubed times 1 meter cubed. Divide by the molar mass. I'll also change it to kilograms. So it is 27 grams. So it is 27 times 10 power negative 3. Then times Avogadro's number, which is 6.02 times 10 power 23. Let's check with our calculator. 2700 divided by 27 exponent negative 3 times 6.02 exponent 23. So this gives you the number of particles as 6.02 times 10 power 28 as required. So here I have used the simpler, what I think to be simpler, by using simple calculations. Otherwise, for those who can use relations, you can now use this simpler method also. From here, if we say 1 mole of aluminium has that, it means 27 grams. 27 grams of aluminium has 6.02 times 10 power 23 atoms. And it means 1 gram has this over 27. And therefore, so 1 gram has 6.02 times 10 power 23 over 27 atoms. That's for 1 gram. From the density 2.7 grams. So remember 2.7 grams is 1 centimeter cubed. 1 centimeter cubed is 2.7 grams. And this will have 2.7 divided by 27 times 6.02 times 10 power 23. These are atoms in 1 centimeter cubed. Then how about in 1 meter cubed? Note that 1 centimeter cubed is the same as 1 over 10 power 6 in meters cubed. How many atoms will this be? So this means in 1 meter cubed, we shall have 2.7 divided by 27 times 6.02 times 10 power 23. This is in 1 centimeter. So in 1 meter cubed, we shall multiply this by 10 power 6. And I think this takes you back to that value there, to the value we have obtained above there. So you can check which one is easy for you. If you're a chemistry student, this should be easy. This should be easy. Okay. So to make 1 meter cubed, we took the 10 power 6 the other side. So 1 meter cubed will have this number of atoms as required. A sample of aluminium. Aluminium foil has thickness 0.090 millimeters. The current is 4.6. The magnetic flux density is 0.15 teslas. Acts at right angles to the foil. Use the value in Roman 1 to calculate the voltage VH that is generated. So this is going to be N, number density. So VH has been given as Bi over NTQ. So just substitute. So this will be 0.15 times the current, which is 4.6, divided by 6.02 times 10 power 28 times the thickness is 0.090 times 10 power negative 3, then times the charge, which is going to be 1.6 times 10 power negative 19. So we press our calculator. So from my calculator, I have got 8.0 times 10 power negative 7 volts. State Faraday's law, the magnitude of the induced EMF in a coil, magnitude of induced EMF in a coil is directly proportional to the rate of change of magnetic flux linkage. Magnitude of the induced EMF of the coil is directly proportional to the rate of change of magnetic flux linkage. Okay, so here we have a solenoid S has a small coil C placed near to one of its ends as shown here. The diameter of the small coil is 3.6 times 10 power negative 2. The coil C has a circular cross-section of diameter that a number of turns 63. The solenoid S produces a uniform magnetic field of flux density B in Tesla in the region of coil C given by that expression. I is the current in amperes in the solenoid S. The variation with time t of the current I in solenoid S is shown in the figure below. State two times at which there is no EMF induced in the coil. 2 times for which there is no EMF induced in the coil. Note that an EMF is going to be induced when there is a change in the magnetic flux linkage. And the change is going to be depending on how the current is changing. The rate of change is going to be determined by the change in current over time. So that is going to be the gradient. So when the current is maximum, it means the flux is maximum. The rate of change is going to be 0 because even at this point here, the gradient is going to be 0. It is a tangent, which is a horizontal line. So there, the flux linkage is maximum. That means the rate of change is going to be 0. At this point, when the current becomes 0, the flux linkage is 0. The rate of change is maximum. Therefore, they said where no EMF is induced, you just look for a point where the current is maximum. That is when the flux linkage is maximum, the rate of change is 0. So we talk about T1, you can talk about T3, you can talk about T5, you can talk about T7. where the current is maximum. Here, here, there, there. The gradient is a horizontal, the tangent is a horizontal line, giving a zero gradient. The rate of change is zero. When the current is maximum, flux linkage is maximum. State the two times at which the induced EMF is maximum, but with opposite polarities. Induced EMF is maximum here, it is maximum there, it is maximum there. But opposite polarities, this one, the gradient here is in the same sign as this gradient. The gradient here is opposite sign to this gradient. So since they want maximum but opposite polarities, maximum but opposite polarities. So it means for maximum and opposite polarities, we have T2 and T4. T2 and T4, that is maximum but opposite polarities, T2 and T4. Alternatively, you can say T4 and T6. You can't say T2 and T6 because T2 and T6, they are maximum and the same polarity because the gradients have the same sign. So it is T2 and T4 or T4 and T6. That is the times for which the EMF is maximum with opposite polarities. The alternating current in the solenoid S in B is replaced by a constant current of 5.0 amperes. Calculate the average EMF induced in the coil when the current in the solenoid is reversed in this time. I said when the current is reversed in that time, it means we have to divide the time by 2. And it is equivalent to multiplying the answer by 2. So the EMF is going to be N times change in flux with the time, which is going to be the number of turns of the small coil. I think it was 63 times, of course, this is the same as N, B, A over time. The magnetic flux density is going to be got from B equals to magnetic flux density is going to be got from B equals 9.4 times 10 power negative 4I. So this is going to be 9.4 times 10 power negative 4, then times I, which is the current, that is 5.0 times the area. The area is going to be pi r squared. So this will be pi. The radius, they gave us the diameter as 3.6, so the radius is going to be 1.8 times 10 power negative 2, and this is squared. That is the area. Divide by the time. The time for reversing was 6 milliseconds, 6 times 10 power negative 3. When I use this time without dividing it by 2, I'll multiply here by 2. And I press my calculator. So from my calculator, I'm getting 0.10 volts. Two significant figures. A horseshoe magnet is placed on a top pan. Balance. A rigid copper wire is fixed between the poles of the magnet as illustrated here. The wire is clamped at ends A and B. When a direct current is switched on in the wire, the reading on the balance is seen to decrease. That means the force on the magnet decreases. The force on the magnet decreases. That means the force on the wire must be in the opposite direction. If the force on the magnet decreases, it means the force on the magnet is upwards. Therefore, the force on the wire must be downwards by Newton's third law. State and explain the direction of the force acting on the wire. So, since the balance reading reduces, it means the force on the magnet is upwards. Since the balance reading decreases, It means the force on magnet, the force on the magnet is upwards. That's why the reading becomes smaller. Is upwards. By Newton's third law, the force on the wire must be downwards because these two wires are equal but opposite. By Newton's third law, the force on the wire must be downwards. Must be downwards since the forces are equal but opposite. So if the reading reduces, it is because the force on the magnet is upwards. That's why the reading is reducing. And by Newton's third law, the force on the wire must therefore be downwards, since the forces must be equal but opposite. State and explain the direction of the current in the wire. Direction of the current in the wire. Since we have now seen that the force on the wire is downwards, then by Fleming's left-hand rule, by Fleming's left-hand rule, since the force is downwards, make the first thumb, the thumb should point downwards. The first finger is pointing north to south. When you rotate the first finger is north to south. When you rotate your hand for the thumb to point downwards, you notice that the second finger points from B to A. So now, by Fleming's left-hand rule, the current is from B to A, in that direction, B to A. First finger, north to south. From north to south, second finger, the thumb should be rotated to point downwards. Then the current is going to be from B to A, as simple as that. Okay. A direct current of 4.6 amperes in the wire causes the reading on the balance to change by, so a DC causes the reading to change by that value. DC causes the reading to change by that value. The DC is now replaced by an alternating frequency current of frequency 40 Hertz. So we have seen that 4.6 DC causes the reading to change by 4.5 times 10 power negative 3 newtons. Okay. Then the directed current is now replaced by an alternating current of frequency that. So the period of this is going to be 1 over 40, which is 1 over 40, 1 divided by 40, that is 0.025. They gave us here in milliseconds, so that is 25 milliseconds. So one cycle is in 25 milliseconds. 1, 2, 3, 4, 5. So we shall have only 2 cycles here. Okay, and so we can find, since we have root mean square value of current, we can now find the maximum force. The maximum force or maximum change produced by this root mean square value. So the root mean square value of current, the maximum force I naught is root 2 times root mean square value of current, I root mean square, which is root 2 times 4.6. So which current now corresponds to this peak? Which force corresponds to this change? The 4.6 corresponds to this change. 4.6 amperes corresponds to this change, then which force corresponds to this one here? If you want, of course, the maximum force or the maximum change in force for alternating is going to simply be root 2 times 4.6 divided by 4.6 times 4.5 times 10 power negative 3. Alternatively, you can use the formulas directly. You can use the formulas. You say for the first one, you have 4.5 times 10 power negative 3 was equal to B. That was B times current, which is 4.6 times the length. For the same wire, the force F max is not known. The magnetic flux density is the same. The current is now root 2 times 4.6. That is the maximum current, then times L. Trying to make F max the subject, or the change in F max the subject, you are going to see that you come up with root 2 times 4.6 over 4.6 times that. So the maximum change in force is actually root 2 times 4.5 times 4.5 times 10 power negative 3. And this is going to give us, press new calculator. So the maximum change in force is 6.4 times 10 power negative 3, which is 6.4 newtons. Okay, so our graph should not go beyond 6.4 on the vertical, either above or below, because it is plus or minus. So 6.4, the scale here is one small box, I guess. So you can put a reference. You should not go beyond one small box along here. Even at the bottom, you should not go beyond 6.4. So now it is time to sketch the graph. Of course, it is sinusoidal. So half of the, we have seen where we have the full cycle. Let's just look for where half a cycle stops. 25 small squares, that is half a cycle. So 12.5, 25 is a full cycle. So 12.5 is half. 11, 12 and a half. This is half a cycle. Then a quarter cycle, so I'll add 12 and a half. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 and a half. That is another half a cycle. Then the remaining part is another half. Then a quarter a cycle, because I want to see where the maximum is. A quarter cycle, I will again divide 12 and a half by 2. Or you say 25 divided by 4. 25 small squares divided by 4. Those are 6.25 small squares. Approximately 6 squares. 1, 2, 3, 4, 5, 6. So this is, that is where I'm going to have the first quarter of a cycle. I can even sketch this. I will increase the thickness. So since it is sinusoidal, so it is going to be like this. The full cycle is here. Okay. Then again, I'll count 6 small squares from here. 1, 2, 3, 4, 5, 6. It is around here. It is around there. So I'll draw a curve. I'll count another 6 from here. 1, 2, 3, 4, 5, 6 and a half. 6 almost here. It goes to maximum. Then it comes back to 0. Then I count another 6 and 1, 2, 3, 4, 5, 6. It's around here. So the maximum here is around here. So we have such a graph. So you should be able to draw such a graph. The approximate values, especially for half a cycle, are very important. For half a cycle, They are very, very important. This is within the box. It is within the box there for half a cycle. Okay, so you can draw such a neat graph, better than mine even. A smooth curve, which is sinusoidal. Okay, a cross section through a current carrying solenoid is shown here. Okay, draw field lines to represent the magnetic field inside the solenoid. Of course, the magnetic field inside is uniform, so I'll just draw straight lines inside. I'll draw straight lines inside. I'll draw one at the center, which is not going to bend completely. Then I will draw others on the sides. Of course, these others, they can slightly bend as you move away. Okay, at least 3 field lines, those are enough. But the field is by the right-hand grip rule. They are saying here current is coming out and the other it is coming into. So if I was to draw if I was to draw a coil here, this would be like that. So you grip the solenoid with your fingers folding in the same direction as that current. In other words, your fingers folding upwards with the thumb points to the left. That means the arrows are coming like this. As simple as that. This is not necessary, so I can remove it. So the field line is supposed to be like that. Okay, state Faraday's law. The magnitude of the induced EMF is directly proportional. The magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. Okay, a coil of insulated wire is wound on soft iron core. The coil is connected in series with a battery, a switch, and an ammeter as shown here. Use laws of electromagnetic induction to explain why when the switch is closed, the current increases gradually. Why not rapidly to its maximum value? When the switch is closed, the current increases gradually. So when the switch is closed, the current increases gradually to its maximum value. Why does the current increase gradually to its maximum value in the solenoid or in the coil or through the ammeter, of course? So there's increasing current in the core, which causes an increase in flux. So increasing current in the core causes an increase in the flux when the switch is closed. So increasing current, in the core. Because you close the switch, the magnetic field grows. Increasing current in the core causes increase in the flux. Increasing current in the core causes increase in flux. And of course, increasing flux again induces increasing flux induces an EMF in the coil. The increasing flux induces an EMF in the coil. Of course, by Lenz's law, this induced EMF opposes growth of current. Thus, it increases just gradually. So, increasing flux in the core induces an EMF in the coil. This induced EMF opposes growth. Opposes growth of current. Thus, it increases gradually. So instead it will increase gradually rather than rapidly. So that is because there's an induced the current in the core causes a magnetic field in the core, which again induces another current in the coil. The induced current in the coil by the core opposes the growth of the current. Thus, it increases gradually. It just increases gradually because of the opposition. Okay, an electron is traveling in a vacuum at a speed of 3.4 times 10 power 7 meters per second. The electron enters a region of uniform magnetic field of flux density 3.2 milliteslas, as shown here. So you notice that when we resolve this perpendicular to the magnetic field, resolving this perpendicular to the magnetic field, this is going to be 3.4 times 10 power 7 sine of 30. The initial direction of the electron is at an angle 30 degrees to the direction of the magnetic field. When the electron enters the magnetic field, the component of velocity Vn normal to the direction of the magnetic field causes the electron to begin to follow a circular path. Find Vn. So we want the component normal to the magnetic field. So Vn is simply going to be equal to 3.4 times 10 power. We have seen it is 3.4 times 10 power 7 sine of 30. We are resolving perpendicular to the magnetic field. When I press my calculator, 3.4 exponent 7 sine 30. This is simply 1.7 times 10 power 7 meters per second. Then calculate the radius. The second part wants the radius. So note that the magnetic force provides centripetal force. So the magnetic force is BQV is equal to mv squared over r. That means r is going to be equal to the squares cancelled. R is going to be mv over bq. We now substitute. It is an electron. The mass is 9.11 times 10 power negative 31. The speed was given, I think. Or the speed which causes that is the component that we have found here. 1.7. This was 31. 1.7 times 10 power 7 divided by the magnetic flux density, which is 3.2 times 10 power, I think it was 3.2 milliteslas. Magnetic flux density is 3.2 milliteslas. So times 3.2 milliteslas, then times the charge, which is 1.6 times 10 power negative 19. Press our calculator. So from my calculator, I'm getting 0.030 to two significant figures as the radius. State the magnitude of the force, if any, on the electron in the magnetic field due to the component of its velocity along V parallel to the magnetic field. V parallel to the magnetic field does not contribute to the force because V parallel to the magnetic field, Fleming's left-hand rule cannot apply. So B parallel to the magnetic field does not contribute to the force. It just contributes to the linear motion. So this is going to be 0. Use information from A and B to describe the resultant path of the electron in the magnetic field. So we have seen the horizontal component does not contribute to the force. It is but it contributes to linear motion. It causes the particle to move in linear motion. Yet the vertical component causes the particle to move in a circular form. So in other words, the path will end up being stretched like a spring. So they said describe the resultant path. So it's a helix. It's a helix. It's a helix or a coil. It's like a coil or it's a helix. The path is a helix. Let me even write this one very well. It's a helix. Okay, state Faraday's law. State Faraday's law. The magnitude of induced EMF the magnitude of the induced EMF in a coil is directly proportional to the rate of change of magnetic flux linkage. Okay, an ideal transformer is illustrated here. Explain why when there is alternating current in the primary, there is a current in the load resistor given here. Explain why when there is a current in the primary, there is a current in the load resistor. So now we should be thinking about the working principles of a transformer. So when there is an alternating current in the primary coil, it creates a magnetic field around the primary coil. The magnetic field is linked by the core to the secondary coil. And the secondary coil, the turns of the secondary coil cut the changing magnetic field, which induces an EMF in it. Therefore, there is a current in the load resistor due to the EMF induced in the secondary coil. Okay, so let's simply say that alternating current, I'll just write AC in primary. Alternating current in the primary coil gives rise to changing magnetic flux. In the core. Gives rise to changing magnetic flux in the core. The changing magnetic flux links with the secondary. The changing magnetic flux in the core links with the secondary coil. Links with the secondary coil, which induces an EMF in the secondary. Which induces an EMF in the secondary. Which induces an EMF in the secondary. Of course, the induced EMF in the secondary is the one which causes a current. So we can simply say induced EMF in the secondary coil causes a current in the resistor. That is precisely why there is a current in the resistor there. Okay, next. The primary coil in B has 2,700 turns. The primary coil has 2,700 turns. The secondary coil has 450 turns. The EMF E applied across the primary coil is given by this. So this must be V naught of the primary. That is the V naught of the primary. E is measured in volts and T in seconds. Calculate the root mean square EMF induced in the secondary. So first of all, we know that the number of turns in the secondary over number of turns of the primary is the same as V. I'll use E for EMF since they have used E for EMF. So this is going to be the same as because this is what is given here is V naught. So what we are going to be calculating is going to actually be a maximum. So this is E naught. Let it be E naught peak. So this will be equal to E in the secondary, which is I'm going to call it E naught, E maximum in the secondary over E maximum in the primary. So this is going to simply be equal to number of turns of the secondary is 450. Number of turns of the primary is 2,700. Note that E naught of the primary is, the peak value of the primary is 220 volts. So maximum EMF of the secondary is going to be 450 divided by 2,700 times 220. That is the maximum value. But we want the root mean square value. So it means E root mean square value is going to be the square root. It is going to be maximum E naught secondary divided by root of 2. So this is going to be 450 times 220 divided by 2,700, again divided by the root of 2. Divide by the root of 2. So press the calculator. So this is giving me 26 volts. You can check 26 volts. Okay. A small coil is connected to a sensitive voltmeter. A sensitive ammeter is situated near one end of the solenoid, as we can see here. As the current in the solenoid is switched on, there is a changing magnetic field inside the solenoid. State what is meant by a magnetic field. So a magnetic field is simply a region of space where there is a force exerted on or by a magnetic pole. Region of space where a force. Region of space where a force is exerted or experienced on. It can be a magnetic pole. You just choose one. It can be a magnetic pole. It can be a moving charge. It can be current carrying wire. And so on and so forth. So that is a magnetic field, a region of space where a force is experienced or exerted on a magnetic pole, a moving charge, a current carrying wire. It can be magnetic material, and so on and so forth. That is a magnetic field. On the figure 8.1, draw an arrow on the axis of the solenoid to show the direction of the magnetic field inside the solenoid. Label this arrow P. So, using the right hand grip rule, imagine you grip the conductor with your fingers folding in the same direction as the current here. So your fingers must point in that direction. The only way you can make your fingers point in that direction is when the thumb is pointing downwards. Therefore, this side is north. So the arrow is downwards, and this is P. So that is the arrow P. They said label it P. Draw an arrow on the axis of the solenoid to show the direction of the magnetic field inside the solenoid. As the current in the solenoid is switched on, there is a current induced in the small coil. This induced current gives rise to a magnetic field in the small coil. State Lenz's law. Of course, Lenz's law deals with direction. Direction of the induced EMF coil is such as to cause effects that oppose the change producing it. Direction of induced EMF is such as direction of induced EMF is such as to cause effects that tend to oppose the change causing it or producing it. Okay, so that is Lenz's law. Use Lenz's law to state and explain the direction of the magnetic field due to the induced current in the small coil. On the figure, mark this direction with an arrow inside the small coil. Of course, that is the easiest. If this is north and this is south, according to Lenz's law, this should be south so that the other one is north, because the direction of the induced EMF causes an effect that opposes the change producing it. When you grip the right hand with the thumb pointing that direction, so the arrow must be pointing in that direction for the second coil, because the induced EMF is always such as to cause effects that oppose the change producing it. If you grip the conductor with the thumb pointing into the north, to the magnetic north, that is upwards, you'll even notice that the current here is going to be in this direction here, but the direction of the current was not required anyway. So the arrow they want was this one here, pointing vertically upwards, because the direction of the induced EMF is always such as to oppose the change producing it. So why is the arrow upwards? I think that's what they want here. 1 mark is for drawing that arrow. So we can say by Lenz's law, of course, we are relating to Lenz's law. The magnetic field in the solenoid is increasing. The magnetic field in the solenoid is increasing when the switch is closed. Is increasing. So by Lenz's law, the field in the coil must be in opposite direction to oppose the increase. To oppose the increase. That is as simple as that. The magnetic field in the solenoid is increasing when the switch is closed. Therefore, the field in the other coil must be such as to oppose this increase. Therefore, the arrow must be in the direction that we have indicated here. Okay. Next. The smaller coil has area of cross section, which is that it has 75 turns. It has 75 turns. A constant current in the solenoid produces a uniform magnetic flux of flux density 1.4 milliteslas through the small coil. The direction of the current in the solenoid is reversed in a time off, so the current is reversed. You either divide the time by 2 or we shall multiply the EMF by 2. So we shall say the EMF induced is equal to the rate of change of magnetic flux linkage, which is N times change in phi divided by delta T. So this is going to be number of turns is 75, change in flux. Our magnetic flux density is 1, of course, flux is BA. Magnetic flux density is 1.4 times 10 power negative 3 teslas. Then times area is pi. The area was given actually 7.0 times 10 power negative 4. Divide by the time is 0.12. Because the current is reversed, I will multiply this by 2. Or I divide the time by 2. When I press my calculator, so this is giving me 1.2 times 10 power negative 3. 1.2 times 10 power negative 3. Okay. Explain what is meant by magnetic field. This question also appear many times until we get used to it. What is meant by magnetic field? So we say the magnetic field is a region of space where there is a force experienced or created. Region of space where there is a force. It can be on or by. There's a force experienced. It can be by a moving charge. It can be by magnetic pole. It can be by or on a current carrying wire or conductor. Okay. Next, the particle has mass m, charge q, speed v. The particle enters a uniform magnetic field of flux density B such that on entry it is moving normal to the magnetic field. The direction of the magnetic field is perpendicular to and into the plane of the paper. So the direction of the magnetic field is perpendicular to and into the plane of the paper. So the first finger points to the table or to the paper on the table. If you hold the paper vertically, then it points to the paper. Because the particle is positive, the second finger points in the direction of the velocity. And the moment you do this, you see that the thumb is pointing upwards. First finger onto the table, second finger to the right, the thumb points upwards. Draw out the path of the particle moving beyond the region of the magnetic field. So the force is vertically upwards. So we shall draw a parabolic path, or the particle experiences a circular path. Draw a very neat tangent to the initial direction, a very smooth curve without any kinks. Me, I'm drawing on a computer. Then when it emerges, you put a what? When it emerges, you put a ruler and draw a tangent. You draw a tangent. Where it emerges, you put a ruler and draw a very beautiful tangent. As simple as that. Note that your curve must be extremely tangential to the initial path. Mine is very hard to draw it neatly because I'm using a free writing on a computer. If you draw yours when it is not tangential, then you lose a mark. Okay, so I have used the Fleming's left-hand rule to arrive at that. The force is upwards because the field is into the page. The first finger was into the page, the second finger was to the right, the thumb pointed in that direction. So that is the direction of the magnetic field. That's why the particle moves upwards. There is a force acting on the particle causing it to accelerate. Explain why the speed of the particle on leaving the magnetic field is still v. Why is the speed still v, yet there is a force acting on it to accelerate? Of course, the magnetic force is perpendicular or normal to the direction of motion. It does not change the speed. So the magnetic force is normal. Is normal to the direction of motion. So it does not change speed. The magnetic force is normal to the direction, so it does not change speed. The particle in B loses an electron so that its charge becomes positive 2q. Its change in mass is negligible. It's almost the same. In terms of v, the initial speed of the particle such that the path through the magnetic field is unchanged. We want the radius to remain the same. So remember, the force due to the magnetic field provides the centripetal force. We want the path not to be changed, so the radius to remain the same. So BQV is equal to mv squared over r, and v cancels. So it means r is going to be equal to mv divided by bq. So the mass is negligible, the change in mass is negligible, so that one we have no problem with it. Then in terms of v, the initial speed of the particle such that its path through the magnetic field is unchanged. So we want r to also be the same. And when you look at this expression here, you notice that the charge q is directly proportional to v. So if the charge has been doubled, the speed should also be doubled. So since Q is doubled, speed should also be doubled because they said explain your working. The first VFB provides FC. I do the algebra. So we want the speed, the radius to be the same, the mass is negligible, the change in mass is negligible, B is the same, so it is V directly proportional to Q. And since Q has doubled, then the speed should be doubled. Speed should be doubled. So the answer here is going to be 2V. The answer there will be simply twice V. Okay. State Faraday's law of electromagnetic induction. We are almost ending these questions. Therefore, we are now in the final stages. So these questions should now have become part of you. Faraday's law. The magnitude of induced EMF. Magnitude of induced EMF in a coil is directly proportional. Directly proportional to the rate of change of magnetic flux linkage. The magnitude of induced EMF in a coil is directly proportional to the rate of change of magnetic flux linkage. Okay. A solenoid S is wound on a soft iron core as shown in the diagram. A coil C having turns 120 of wire is wound onto one end of this core. The area of cross section is 1.5 centimeters squared. A hollow probe is close to the other end of the core. When there is a constant current in solenoid S, the flux density in the core is 0.19 teslas. The reading on the voltmeter connected to the hollow probe is 0.2 volts when there is a constant current. The current in the solenoid is now reversed. So the current is now reversed in that time. Calculate the reading of the voltmeter. Since the current is reversed, induced EMF. The induced EMF is going to be equal to the change in the flux, that is the change in NBA with the time. So this is going to be, since the current is reversed, we shall multiply this by 2. So this is going to be 2 times number of turns is 120. Magnetic flux density is 0.19. Cross-sectional area, they gave us 1.5 centimeters squared, so it will become 1.5 times 10 power negative 4. To change it to meters squared, this is divided by the time, which is 0.13. Note that I have multiplied by 2 because the current is reversed. Otherwise, I wouldn't multiply by 2. Press my calculator. So from my calculator, I get this as 0.053 volts when the current is reversed. Okay. So complete the figure for the voltmeter readings for the times before, during, and after the direction of the current is reversed. During, we have seen that during the reverse, during current change, when current is 0, of course, the reading of the voltmeter will be 0.053 during current change when the current is 0. The reading of the voltmeter is 0.053 when the current is reversed. Okay, that is from maximum to 0. And then, of course, when during the process of changing, the reading on the voltmeter connected to the hollow probe will read 0 because when the current is reversed, when the current becomes zero, the reading of the voltmeter is going to actually be zero, because the EMF, the magnetic flux density is going to become zero at that point when the current is zero. The magnetic flux density will be zero, so the reading of the whole voltage will be zero. Then number two, before current changes, current is constant. When the current is constant, the induced EMF is going to be zero. So here it will be zero. After current changes, it again becomes constant. The induced EMF again becomes zero. So before current changes, it is constant, it is zero. After current changes, it again becomes constant, induced EMF is zero. So coil C, the voltmeter shows zero. Now, for the hollow probe, before current changes, the reading of the voltmeter of the hollow probe is zero. When current changes, during the current change, when the current becomes zero, the reading of the voltmeter becomes zero. Then after it has changed, then there should be a change in direction. So the reading of the voltmeter should now be opposite. So this should be negative 0.20 volts. Negative 0.20 volts. So that is simple logic. That is logic. That is application of understanding of the concept of magnetic flux density, hollow probe, and Faraday's law. Then define magnetic flux density, that is B. Determine magnetic flux density B. Remember, B is going to be F over I L sine theta. So we can say if sine theta is 1, then theta is 90 degrees. So we shall say the force per unit length. The force per unit length, we can also say per unit current. The force per unit length per unit current. The force per unit length per unit current, per unit current on a long straight conductor carrying a current because it's per unit length per unit current. That one I don't even need to repeat myself. Carrying a current normal to a uniform magnetic field. So that is magnetic flux density, force per unit current per unit length, force per unit length per unit current on a long straight conductor carrying a current normal to a uniform magnetic field, where now sine theta becomes 1. Okay. A stiff copper wire is balanced horizontally on a pivot as shown here. So you see it is balanced horizontally as shown here. Section PQ and QR and RS of the wire are situated in a uniform magnetic field of flux density B produced between the poles of a magnet. The perpendicular distance of PQRS of that plane is 7.5 centimeters. When a current of 2.7 amperes is passed through the wire, a small mass of 45 milligrams is placed at distance 8.8 centimeters from the pivot in order to restore balance. So in other words, this mass is the one which is restoring balance. So the diagram is now again drawn here with the plane of the wire into the magnetic field. Okay, explain why when the current is switched on, the current in the sections PQ and RS of the wire does not affect the balance. Of course, now Fleming's left-hand rule. Let's say this is north and that is south. So if the field is in that direction, The first finger is in that direction. The current is upwards. The second finger must be upwards. You notice that the thumb is into the page. That is in the horizontal plane. The thumb is in the horizontal plane into the page. Here the current is downwards. The first finger is in the same direction, north to south. The second finger points downwards. So this is into the page. This is in this direction. So they are in opposite direction, and they are going to be equal in magnitude in the same plane. They do not affect equilibrium. So we are saying the force on PQ and RS are horizontal. The force on PQ and RS are horizontal. Hence they create no moment. Hence they create no moment about the pivot. For them, they are in the horizontal plane, so they will create no moment about the pivot. Therefore, they don't distort equilibrium. Alternatively, you can think of the forces being equal and opposite. Hence, the net force on these two sections is 0. So we can also say that the force on PQ and RS are equal and opposite. They are equal and opposite. Hence, there is no net force. There is no net force on the two sections. Okay, next, the length of section QR of the wire is 1.2 centimeters. So this length is what is very important because the current here is flowing in this direction. If you use Fleming's left-hand rule, the first finger in that direction, reversing the current to point from R to Q, the second finger to point from R to Q, the force here is vertically downwards. So it means that is the force which is distorting balance. So we are going to take moments about the pivot. So taking moments about the pivot. The force on this wire is given by Bill, so that will be Bill. I'll just write Bill. Perpendicular distance is X. I'll just call it X times X. Should be equal to, that will be anti-clockwise moment. Then the clockwise moment is going to be caused by this weight here. So that will be the weight, which I will call W, which is M times G times the perpendicular distance, which I will call Y. So let me substitute. B is not known. The current flowing is 2.7. The length of the section is 1.2 centimeters. So that is 1.2 times 10 power negative 2. The perpendicular distance is from the end of the plane is 7. This is the perpendicular distance, 7.5 times 10 power negative 2. This should be equal to the mass which is balancing the other side, and the mass was 45. The mass was given as 45 milligrams. So we shall say times, this is equal to 45 times 10 power, because it is in milligrams. 45 milligrams. Changing from milli to grams, this will be 45 times 10 power negative 3. Again, changing from grams to kilograms will be another times 10 power negative 3. So this becomes negative 6. Then times G, which is 9.81. Then times perpendicular distance, which is 8.8. Perpendicular distance is 8.8 centimeters. So that is 8.8 times 10 power negative 2. So I will just press my calculator without wasting time to divide both sides and find B. So from my calculator, I am getting 1.6 times 10 power negative 2 Teslas. Okay. A hollow probe is placed near one end of a solenoid that has been wound on a soft iron core as shown here. Okay. The current in the solenoid is switched on. It is direct current. The hollow probe is rotated until the reading VH on the voltmeter is maximum. The current in the solenoid is then varied, causing the magnetic flux density to change as shown here. So the variation of T with the magnetic flux density is shown here. At time t equals to 0, the whole voltage is V naught. At t equals to 0, the whole voltage is V naught. Okay, so we start with V naught at t equals to 0. On the figure, draw a line to show the variation with time t of the whole voltage for time t equals to 0 to time t equals to t4. So we know that VH is equal to BI over NTQ. So we notice that VH is directly proportional to B when the current is constant. So it means the graph is going to be the exact replica of the one which we have. So at t equals 0, V is V naught. It changes only at t equals t1. So I will draw a horizontal line here. And when B is constant, VH is constant. So we have a horizontal line along V naught. So I will increase the thickness here. So I will draw a horizontal line. It's not very beautiful. So that is there. And also at T3 to T4 it is constant, but it is, you notice that here at t equals 0, when B was 1 millitesla, VH was V naught, that means that negative 2 should be twice. So this will be twice V naught. So between T1 and T4, that should be horizontal line. Why is it hard to draw this line? Okay. So now I just join because the remaining part is the same. I told you that VH is very directly proportional to B. So I just join the two parts. Just join the two parts. It is just the exact replica of the first one. Okay. The hollow probe is in A is now replaced with a small coil. The hollow probe is now replaced with a smaller coil of wire connected to a sensitive voltmeter as shown here. So we have replaced the hollow probe with a small coil. Okay. So an EMF is going to be induced there, just in case. The magnetic flux density normal to the plane of the small coil is again varied. So they are changing the magnetic flux density, and it is varied the same way it is varied in the previous case. So if we are now find the graph we are going to draw is for induced EMF E, and an EMF is only induced when there is a change in magnetic flux linkage. So induced EMF is directly proportional to the change in magnetic flux linkage. Now remember, flux depends on B. Now when B is constant, it means the flux linkage is constant, is not changing. EMF is going to be 0. So here where B is constant, EMF is 0. Where B is constant, EMF is 0. It is only changing between these points here. And here it is a constant gradient. So it is just going to be one step. It is a constant gradient. It's just going to be one single step. So I'll represent this part here with a constant EMF. Here the EMF is constant, not 0. It is not 0, and constant. It is constant. So I just come here and draw. Where B is constant, between 0 to T1, the EMF is 0. And between T3 and T4, the EMF is still 0 whenever B is constant. So here, that is 0. Here between T3 and T4, there is no induced EMF because there is no change in magnetic flux. It is only changing between T1 and T2. So, and since it is a straight line, then it is also constant here, but not 0. So I'll just draw another horizontal line here. So using a ruler, you can draw a very nice step. Using a ruler, you can draw a very nice step. Okay, so that is the graph. That is the graph. Note how we arrived at it, not just a matter of drawing it. We said E is going to be a change in magnetic flux NBA with the time. We are relying on B. If B is also constant, then the magnetic flux linkage is constant. So E is going to be not is going to be 0. When B is constant, E is 0. When B is changing, the magnetic flux linkage is changing. So it means the induced EMF there should be an induced EMF. Okay. Define magnetic flux linkage. Define magnetic flux, that is BA. So we now know that the magnetic flux is the product of the magnetic flux density and the area. The area normal to the direction of the flux. Or the direction of the field, that is the magnetic flux. Or you can define it in terms of B times A times sine theta. Define sine theta as the angle between the direction of B and the plane of the area. That is magnetic flux linkage, magnetic flux. Faraday's law, the magnitude of the induced EMF, say in a coil, is directly proportional to the rate of change of magnetic flux linkage. That is Faraday's law. The magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. A solenoid has a coil C of wire wound tightly about its center as shown here. Okay, we have seen this. The coil C has 96 turns. So C has 96 turns. That is, the coil here has 96 turns. The uniform magnetic flux phi in Weber in the solenoid is given by this expression, where I is the current. Calculate the average EMF induced in the coil when the current in the solenoid is reversed. In that time, the current is reversed. So EMF induced is going to be equal to change in flux, that is N times change in flux divided by time, or B or NBM. So this is going to be, the number of turns was 96 times, the flux is going to be 6.8 times 10 power negative 6 times the current, which is 3.5, divided by the time is 2.4 times 10 power negative 3, but it is reversed, so we shall multiply this by 2. I'm on to my calculator. So this is giving me 1.9 volts. Two significant figures. The DC supply in the figure is now replaced with a sinusoidal alternating supply. Describe qualitatively the EMF that is now induced in the coil. So if it becomes sinusoidal, it keeps changing direction, it means even the EMF induced in the coil must keep changing direction. It should vary from maximum positive from 0 to maximum negative with the same frequency as that of the supply. So since we replaced the DC with alternating, then the EMF induced varies from the maximum value or maximum positive maximum value to 0, then to a negative maximum value, with the same frequency as the supply. So they will have the same frequency as the supply. The induced EMF will have the same frequency as that of the supply. But of course, they could be out of phase. A rigged copper wire is held horizontally between the pole pieces of the magnet as shown in the figure. Look at the figure, the side view and the top view. Top view is viewed from top. So from the width of each pole is 8.5, as we have seen that the width is 8.5. The uniform magnetic flux density B in the region between the poles of the magnet is, so magnetic flux density is 3.7 and is 0 outside. The angle between the wire and the direction of the magnetic field is theta, as we have seen here. That means when we resolve the field perpendicular to the wire, it is going to be sine. Okay, the current in the wire is in the direction shown. By reference to side view of the figure, state and explain the direction of the force on the magnets. By reference to side view, so the field is from north to south. The first finger is in that direction. The second finger is in the direction of the current. So by Fleming's left hand rule, when you place your first finger in that direction and the second finger in this direction, the thumb is pointing upwards, so it is out of the page. The force on the wire is upwards. The force on the wire is upwards. So we are saying, using Fleming's left-hand rule, by reference to the side view, state and explain the direction of the force on the magnets, not on the wire. This is on the magnets. So using Fleming's left-hand rule, using Fleming's left-hand rule, the force on the wire is upwards. And now by Newton's third law, and by Newton's third law, the force on the magnets is downwards, because the force must be equal and opposite. So by Newton's third law, the force must be downwards. If the force on the magnets must be downwards, if by Fleming's left-hand rule the force on the wire is upwards, to balance it, the force must be downwards on the magnet. The constant current in the wire is 5.1 amperes. For an angle theta of 90 degrees, calculate the force. The force on the wire is going to be given by B. Since sine theta, B sine theta. Because theta is 90 degrees, we shall ignore that. This was given at 3.7 milliteslas, so 3.7 times 10 power negative 3. The current is 5.1, and the length was 8.5 centimeters for the width, the length of the magnets. So that's the same length of the wire which is in the magnetic field. So that is 8.5 times 10 power negative 2. When I press my calculator, this is giving me 1.6 times 10 power negative 3. The angle theta is changed to 60 degrees. The length of the wire in the magnetic field is given as that. Calculate the force on the wire. That is not a physics question, it is mathematics. Since the force is given by B sine theta, so we are just substituting. So this is going to be B, which is 3.7 times 10 power negative 3. The current is still the same, 5.1. The length is now 8.5 over sine of sine 60 centimeters. So I will say times 10 power negative 2. Then times sine of the angle, which is sine 60. So sine 60 is going to cancel with that. So this takes us back to the previous part. So this is still 1.6 times 10 power negative 3. It is the same. The constant current in the wire is now changed to an alternating current of frequency 20. So we can predict the period. If the frequency is 20, so the period is going to be 1 over 20. 1 divided by 20, that is 0.05 seconds. And root mean square value of 5.1, we need now to find the peak. Root mean square value of 5.1, we need to find the peak value of current. So the peak value of current, the peak value of force, if the root mean square value of current is that, and this was correspond to a force of 5.1 was correspond to a force of 1.6 times 10 power negative 3 newtons that we calculated earlier on. How about it now we find the peak value of alternating current. This is going to be root of 2 I root mean square. No, I want the peak to find the maximum force. So I naught is going to be root of 2 times 5.1. That is the peak current, which force corresponds to this. So if 5.1 corresponds to that, then which force corresponds to this peak? 5.1 amperes corresponds to that, which force corresponds to that. So it means the maximum force is going to be either positive or negative. So it will be root of 2 times 5.1 divided by 5.1 times 1.6 times 10 power negative 3. So just to use relations, just compare. So this is giving me a root of 2 times that. So root 2 times 1.6 exponent that. And this is giving me 2.3 times 10 power negative 3 newtons. So now it is time for us to sketch. Remember, we saw that the period was 0.05 seconds. The maximum force should be that, either plus or minus. So you now start thinking of how to organize your graph. I'll try to maximize this so that sketching becomes easier for me, at least that. Okay, so the maximum force up should be the same as that at the bottom, since there is no scale, nothing like a scale to use in the bottom. So they wanted us to sketch a graph to show the variation with time t of the force on the wire for 2 cycles. We don't need number of cycles on the vertical, so I'll just choose like 10 small squares to be my maximum. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That will be small. Let me add 11, 12, 13, 14, 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So my graph should not go beyond this line here. My graph will not go beyond that line. My graph will not go beyond that line, because that is the maximum force. So this is 2.3 times 10 power negative 3. Negative 2.3 times 10 power negative 3. Okay. Now on the x-axis, I will also divide. The period is 0.05. I want only 2 cycles. So 0.05, if I use 20 small squares for 1 cycle, then I use 10 for half. So I will say after 5 small squares, 1, 2, 3, 4, 5. That will be maximum. 1, 2, 3, 4, 5. That is half a cycle. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 1, 2, 3, 4. This is 0.05. 1, 2, 3, 4. This is going to be 0.10. If you want, you can continue. I can add 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So I have, this is again 0. Okay, so at a quarter cycle, the force is maximum. Then half a cycle, it goes to 0. So here it should be maximum. I hope I counted the boxes very well. So somewhere here it is maximum. Then it goes to 0. Again, somewhere here it is maximum. Then it goes to 0. Or you can do a better one. Somewhere here it is maximum again. Maximum. Then it goes to 0. Again, it will be maximum somewhere here. Then it goes to 0. Those are already 2 cycles at least. You can add if you want, but they wanted only 2 cycles. So you can draw more than 2 cycles if you want. Okay, so that will be the graph. That will be the graph. Just to make it a little bit visible, more visible. So you can draw a better graph. You can draw a better graph in your book, or I mean on your paper, which is better than mine. Okay, so a scale on the x-axis is the only important thing here, but it should be a sinusoidal wave. They wanted only 2 cycles. They wanted only 2 cycles. I drew more than 2. You can draw only 2 cycles. Okay. State Faraday's law. The magnitude of the induced EMF in a coil is directly proportional to the rate the magnitude of the induced EMF in a coil is directly proportional to the rate of change of magnetic flux linkage. That is Faraday's law. A coil of insulated wire is wound on to one end of the ferrous core and connected to the battery as shown here. So we have a coil of insulated wire, meaning that there is no direct contact. We have a ferrous core that is actually iron. An aluminium ring is placed. On the core and can move freely along the length of the core. The switch is initially open. Use Faraday's law and Lenz's law to explain why the aluminium ring jumps upwards when the switch is closed. Of course, when the switch is closed, a current flows in the coil of wire, so it creates a magnetic field, a changing magnetic field in the ferrous core. The changing magnetic field in the ferrous core induces an EMF in the aluminium coil. So there will be an EMF in the aluminium coil which causes a current in the aluminium ring. The current in the aluminium ring also causes a magnetic field which opposes the change producing it. Therefore, we just play around with Faraday's law and Lenz's law, as simple as that. So we are saying the current in the coil produces changing flux, produces a changing flux by Faraday's law. By Faraday's law, the changing flux induces an EMF. The changing flux induces an EMF. The changing flux induces an EMF. An EMF in the ring. So the current, when we close the switch, produces a changing flux which goes to the ring. Changing flux is going to induce an EMF in the ring. That is in accordance with Faraday's law. But then the current in the ring causes a magnetic field around the ring. The current in the ring causes a magnetic field around the ring. And by Lenz's law, by Lenz's law, the magnetic field around the ring opposes the field around the coil. And by Lenz's law, the magnetic field around the ring, opposes the field around the coil. That's why now we see the aluminium ring jumping. When the switch is closed here, there's a magnetic field in the coil which spreads through the core. Therefore, there's a changing magnetic field in the aluminium ring. The changing magnetic field induces an EMF in the ring, and therefore there's a current in the ring. The current in the ring causes another magnetic field around the ring, and by Lenz's law, the magnetic field around the ring tends to oppose the magnetic field due to the coil. That's why the ring jumps. Okay. Explain how a uniform magnetic field and a uniform electric field may be used as velocity selector for charged particles. So the easiest is to draw a diagram. To write fewer things, you draw a diagram. So we need an electric field, a uniform electric field. So I have parallel plates. Let's say the upper plate is positive, the bottom plate is negative. I'm going to choose a positively charged particle entering horizontally in a uniform. So we have a positively charged particle with speed v entering horizontally in a uniform electric field. If it is entering horizontally, it is experiencing a force due to the electric field downwards. Therefore, it should experience a force due to the magnetic field downwards for the velocity to be selected. So the magnetic field is going to be into the page. So I will say the B field is into the page. The B field is into the page. So we are simply saying that the electric and magnetic fields are placed at right angles to one another. The electric and magnetic fields are placed at right angles to one another, to one another, as we can see in the diagram. Of course, many times when I draw the diagram, I don't write all this. The electric and magnetic fields are placed to one another. The fields are adjusted. The fields are adjusted. The fields are adjusted so that the force due to the magnetic field is equal to the force due to electric field. For no deviation, no deviation for selected particles. There will be no deviation for selected particles with the speed v is equal to E over B. So particles with the speed v is equal to E over B are going to be selected. So it is now operating as a velocity selector. Part B. So we are saying electric and magnetic fields are placed at right angles to one another. The fields are adjusted so that the force due to the magnetic field is equal to the force due to the electric field. There is no deviation for the selected particles with speed v equals to E over B. Particles having mass m and charge q and charge 1.6 exponent 19 pass through a velocity selector. They then enter a region of uniform magnetic field of flux density 94 milliteslas with a speed of 3.4 times 10 power negative 4 meters per second. Okay, this is the diagram. You can look at the diagram. The direction of the uniform magnetic field is into the page and normal to the direction in which the particles are moving. The particles are moving in a vacuum, in a circular arc of diameter 15 centimeters. Show that the mass of one of the particles is 20 U. So note that the particles are moving in a circular path. So we say that the magnetic force is providing a centripetal force. The magnetic force provides centripetal force. Therefore, we shall say BQV is going to be equal to mv squared over r, making m the subject, m is going to be bq times r divided by v. We substitute the magnetic flux density, I think it was 94 millitesla, so that is 94 times 10 power negative 3. The charge is 1.6 times 10 power negative 19 coulombs. The radius, the diameter is 15, so the radius is 7.5 times 10 power negative 2. Then we divide this by the speed. I'm dividing by the speed, which was 3.4 The speed was given as 3.4 times 10 power 4, but they want the mass in U, so I will again divide by 1.66 times 10 power negative 27 to change the mass into U. So this is in U. So when I press my calculator, 94, 1.6, 7.5, 3.4, 1.66. So I get 19.99. So this is 19.99, which is approximately 20 U. We can write the mass in U to one significant figure. On the figure, sketch the path of a uniform magnetic field of mass of a particle of mass 22. You're having the same charge, same speed. So same Q, same V. The mass is larger. So you notice that the larger mass is directly proportional to the radius. Mass is directly proportional to the radius. So the mass is larger, the radius of the path is going to be larger. So if it enters initially from the same point, so we are going to draw another path with a larger radius. So that will be the new path with a larger radius, because the mass is higher and the mass is directly proportional to the radius. Last question, we are almost getting done. We're on the last question. State what is meant by magnetic flux linkage of a coil. Note that magnetic flux linkage has been got from NBA. So it is the product of the magnetic flux density, the number of turns, and the area. And area normal to the magnetic flux density. Or the area normal to the magnetic field. That is the magnetic flux linkage. Okay, next, a coil of wire has 160 turns, so number of turns is 160. Diameter 2.4 centimeters. A uniform magnetic field of flux density 7.5 milliteslas. The direction of the magnetic field is along the axis of the coil. The magnetic flux density is reduced to 0 in that time. So it is reduced to 0, there is no reversing. Show that the average EMF induced in the coil is that. So EMF induced is going to simply be magnetic flux linkage over time. The number of turns was 160. The magnetic flux density was 7.5 milliteslas, so that is 7.5 times 10 power negative 3. The area, they gave us the diameter as 2.4. Area is going to be pi r squared. So that will be pi times radius, which is 1.2 times 10 power negative 2, and it is squared. Divide by the time for which it is reduced, it is 0.15. Press my calculator to check. So from my calculator, I get 3.6 times 10 power negative 3 volts, which is approximately 3.6 millivolts. Last but not least, The magnetic flux density B in the coil in B is now varied with time t as shown here. Use data in B to show. In B we have for a time of 0.15, for a time of 0.15, the induced EMF is 3.6 millivolts. Let's check. 0 from here to 0.1 and here it is 2.5, so this time is 0.15 seconds. So here the EMF is 3.6 millivolts. There the EMF is 3.6 millivolts. So we're going to use that to sketch a graph variation with the time of the EMF induced in the coil. So the time is the same. So between 0.1 to 0.25, 1, 2, 3, 4, 5. Here the induced EMF, because it was, note that the EMF is going to be directly proportional to the rate of change of magnetic flux linkage. Where B is constant, when B is constant, it means EMF is going to be 0. That is the case between, this is the case between, we have seen between t equals to 0 to t equals to 0.1. Between t equals to 0 to t equals to 0.1, so here EMF is going to be 0, here EMF is going to be 0, and here EMF is going to be 0. So we can draw horizontal lines there. Between t equals to 0 to t equals to 0.1, the EMF is 0, so I draw a horizontal line. I'll use my ruler. Then between 0.25 to 0.35, I guess, 0.35, 1, 2, 3, 4, 5. So here again the EMF is 0 because the B is constant and it was 0. Then after 0. What was that value? Let me check the time. 0.3, 1, 2, 3, 4, 5, that is fine. Then here it is in the middle here, 0.4, 1, 2 and a half. It is here. 2 small squares and a half. So I have to check that. 0.4, 1, 2 and a half. So here it is again 0 up to 0.55. 1, 2, 3, 4, 5. So my graph will stop here. So there the EMF is 0 because B is constant. But then for the first part, between 0.1 to 0.25, the EMF changed by, the EMF was 3.6 millivolts. So we look for 3.6. So the scale here is 2/5, which is 0.4. So this is 2.4, 0.8, 3.2, 3.6 is along here. So 3.6 is along here. So I'll draw a horizontal line here. Okay. Then here, of course, the gradient, you see that the gradient is has the same sign. This is positive, negative gradient, this is negative gradient. The gradient has the same sign, so the EMF is not changing direction. Even though B is in opposite directions, the EMF is not changing direction. So the steps are going to be on the same side. However, notice that this gradient here, we are changing from the same value as before, but this time in a smaller value of time. So this is actually half of the time. This gradient is twice the first gradient. This is half, almost half of the time. So this gradient is half of the first gradient. So the EMF here is going to be 2 times the other one at the other point, 3.56 millivolts. So this is going to be 7.2. So the EMF here is going to be twice. So it is going to be 7.2 because the gradient in the second part is twice. The sign has not changed, so it is supposed to be on the same side. So since these are, I'm just going to leave two small squares on top to reach 7.2. Not two small squares. Yes, two small squares. So this is 7.2 somewhere there. This line is supposed to be in the middle of this box, so I'm trying to make it in the middle. It is not easy. Okay. And this one is at 1, 2, 3, 4, 5. Okay, so that will be the very perfect graph. It is a very nice graph. And I think this marks the end of magnetic fields. Our next unit will be alternating current. See you in SC. I hope you have enjoyed this, and I hope we meet in SC. SC I will record short videos starting tomorrow, starting on 24th. See you. Have a beautiful day. Bye bye.